right, everybody, could we get you guys seated and we'll get started in just a minute? Thank you.
Good morning. Hey, good morning. We're going to get started. So I'll introduce myself. I'm Chad Fisher. I work at the Division of Drinking Water in the Fresno Field Office, and I am the Visalia District Engineer, and so that means that I work with primarily disadvantaged communities, many of them struggling with drinking water challenges in Kern, Kings, Tulare, and Fresno counties. So again, welcome. There's a few housekeeping items that I need to go over. We need to talk about the fire exits. So there's a couple in the back, on the sides, and so if everybody could take a second to identify a couple that are close to you. In the event of a fire alarm, we all need to exit the room and exit the building, and I believe the protocol is to walk across the street into the park. At least the last time I was here and there was a fire drill, that's what we did. So another housekeeping item is there is drinking fountains and restrooms kind of out and then out here to the left. And then there's food services on the first floor. We have comment cards in the back. There's on the back table. You can complete those comment cards and then just leave them there on the back table if you like. And we may eventually get a box there. So if there's the box, drop them in there. You can also email comments as we're going today. Michelle is going to be managing that email. It is auditorium@calipa.ca.gov. And I guess I want to say that we have an excellent panel, not only here in the morning and then the afternoon. And I think our goal here is really to share information and to ensure that that our needs assessment funding is used in, the most efficient manner, and that we all, again, share information and share ideas and have a lot of really great discussion. So we are going to, as far as questions go for the panel presentations, we're going to hold questions until after each panelist is finished with their presentation, and then we're going to take 1 or 2 questions immediately after, and then we'll save other questions for a question period that's at about 3 or 3:15 in the afternoon after all of the panelists have spoken. And with that, I'm going to introduce the Deputy Director of the Division of Drinking Water, Mr. Darren Plahimis. Darren also served as the Deputy Director of Division of Water Quality and the Division of Financial Assistance and Administrative Services, and Administrative Services. He's a civil engineer and with a bachelor's in agricultural engineering from Cal Poly San Luis Obispo. Thanks, Darren.
Thank you, Chad. Sort of works. Maybe. Did you do it? All right, you'll do it for me. All right, next slide. Welcome, everybody. So thank you for coming, and those of you that are tuned in, listening in. We're going to kick off here with just kind of some background of kind of what step this is in the 3-step process. So let me start first with, this is all started with the Budget Act of 2018. Approximately $3 million was appropriated for this effort to do basically a needs analysis and further some of the work that had been done with some really rough estimations from existing data before. The intent of the funding now is to try to dig in deeper where we didn't have data and use the funding to generate information that wasn't available so that we can further refine the needs estimate for drinking water systems in California. The funds have to be encumbered by next June, actually even before that with the really administrative requirements. So we're moving as fast as we can, obviously, to just get this underway. Everybody's got this question hanging out there as to what they want to know more details about this. So that's kind of the genesis. Next slide. So we've already done 2 workshops. Workshop number 1 was focused on public water systems serving more than 15 connections, so the ones that are within the regulatory construct of the Safe Drinking Water Act of both the federal and California version, and under state regulation and county LPA regulation from that standpoint. Workshop number 2 dove into some questions for private domestic wells and state smalls, and trying to come up with reviewing what information was available and what work had already been done in that space to try to then develop modeling approaches of estimating drinking water wells, private domestic drinking water wells that could be impacted and might need assistance, and thus would contribute to the needs analysis. And here today we are at workshop number 3. This is where those first 2, where we can identify the systems and identify the locations of well clusters and whatnot that would need efforts, now becomes a cost estimate. And that's what we're looking forward to talking to you about today. So the agenda this morning is really considering historical cost calculations that have been done to give us some background and previous and current needs assessments. This afternoon, we're going to go into activities to research understanding to decrease costs. So I think that's an important point to pause on a moment. We really don't want to do some of the techniques that have been done in the past, where we assume everybody that's got a nitrate problem does nitrate treatment. There are other cost avoidance techniques that happen. You might consolidate, you might find a new source, and those really complicate an estimate when you're getting to it, but are the more realistic approach, rather than, hey, everybody's going to put on treatment costs, we know what the O&M costs are, and we go from there. So we're really trying to push the boundaries of understanding that we are going to make this kind of a more efficient utility delivery system for water, and then as a result, what does that cost, rather than coming up with a really big scary number that presumes that we're going to, and that even presumes that systems could afford that afterwards. So quick on the finger, Michelle. Don't make me jump. I haven't had that much caffeine. I'm not twitchy. Okay, so also this afternoon we're going to get into these other components of disposal costs, understanding the solution, the limitation set, and basically look forward to an open discussion of some of the best approaches here, because I think we are bending into some new ground from at least my purview of what has been done for cost estimation, and so we all hope to be educated greatly on that. Now, next slide. Okay, so nationally, there's a lot of things going on in this space as well. California is not alone here. There are other states that are venturing into this very same area. There's a lot of asset management approaches that are being taken, some on the East Coast. And so this is just a little hint at that we're going to contribute to this conversation just like the other states are, but we need to look what others are doing as well in that space. Okay. Public process. So this is part of the public process that we need to do to develop the needs concept. We want to basically get out kind of an overall plan after this workshop concludes and we've had time to digest all three of them. We'll seek public comment on that in a written fashion and then go forward and kind of put out there so that everybody can see what we're proposing to move forward with. Next. So here's the three elements, again, that we kind of talked about that the workshops mirrored, right? So number one, identifying public water systems at risk or that are failing. And I think the at-risk part is the most work, right? The only one of all of these sets that we're looking at, the one that we know the most about are the ones that are failing. We have those in our system. We know who they are. It's the ones that are coming tomorrow. Interestingly enough, I asked staff to do kind of a flux. How many come onto our human right to water list and how many go off over time? And so to give you some context, historically, that number has bounded between 350 and 250 water systems. So are they the same ones or are they not the same ones? And the answer that came back was, actually the flux is pretty high. It's almost like 50 to 60 systems come on and go off in some proportion of that. So we really have to then get ahead of the curve and like, who are those 50 and 60 that are gonna show up in the near-term approach? And that obviously is a hard exercise to do, and we're entering new space in that regard. The second element of identifying the small water systems and the clusters, I think we have a really good running head start on that with all the work that's been done over the years of GAMA and the USGS and others. So it'll be an interesting exercise to bring that together. And then today's conversation about the cost analysis and element number 3 of this whole work then brings all those together. Okay, so we have identified the problems that we know of. We're anticipating the problems that are going to arrive. What's that going to cost us to address those as a state? And that's really where the rubber hits the road on all of this. All right, next slide. So this is a little more detail on element 1. It does show that the risk analysis type kind of we're proposing here. Looking at connection size, I think, is one of the key things that we're going to use to help filter the workload, really focusing on sizes of the small end, which actually are the most of our systems when we get down to that. I think over 70% of the systems, the drinking water systems regulated in California, fall below that 3,300 connection line. So it really is a large number, and we're not really limiting it. We also then can say that, look, if you're a large system, we don't tend to have much problem with them, or if they do run into problems, they're relatively quick to address it, and that's not where we're talking about focusing work of the Safe Affordable Drinking Water Fund. So you can see how we've broken that out. Next. All right, element number 2, the small systems at risk and clusters of that. This is again, workshop number 2, and where we're headed with that is working a bit off of USGS work to digitize a lot of the wells in California and then do some cross-mapping between the GAMA data we have for water quality and cluster analysis of are there clusters of water systems that we could conceptually bring together as a water system so that people can be off their wells and open that type of public discussion. So I don't know of any place that that's been done yet, so this will be interesting space for us to go into. And number 3. Today's approach, we're going to learn a bunch today about methodology and unit costs and how we're going to go about this. So I'm really looking forward to learning these components today. But key points to remember is that we are wanting in these models not short-term, but really long-term solution model sets. So that is a key component to keep in mind. And we really want to then have a final kind of, after we've estimated the need, we need to then do some work to see how that fits with existing funding models and what potential funding models we may need to have in the future. So we have extensive programs with the Drinking Water SRF, and we've had GEO bond grant monies over the past. Those do great for capital works, not the type of work we need the Safe Affordable Drinking Water Fund to work. So one of the end questions is just not how much money do we need, but then what flavor of money does it need to be, or what color? Affordability. This is a good point to make. We've been really focusing here, and this is, in fact, it's even restricted to the needs assessment from a community standpoint, not individual affordability. So individual affordability does exist in all systems of all sizes, and that's a question for another day. What we're really trying to do in this effort in an initial phase is how do we make a water system in a sense affordable for the bulk of its users, or in an affordable sense so that it's, can meet that test of the community at large from a relatively standpoint can sustain it. This gets tricky in a lot of our smaller communities where, the whole community is disadvantaged, and how much they can afford can really be a question. So we really need to focus on finding sustainable, efficient solutions that are resistant to some kind of perturbation later that can then send them right back to where we're at. Next. Methodologies for costing. There's a bunch of questions we posed here that we hope the panels can address. How long should the cost-affecting consideration be done? How far is reasonable for consolidation? So how far should we be stretching pipelines? I will just throw out there that to try to stretch the imagination, I have spoken with some folks from Iowa who think that 18, 20 miles is no big deal because they do small diameter pipe for in-house use only. So there's no fire flow, there's no landscape, and they're delivering water to address a nitrate need. So we might want to consider different models that we haven't done in California, as well as we're getting into those type of questions. How do we deal with political boundaries? These become really thorny issues on the local planning level, but they do factor then into solution sets that we can consider in costs. How do we account for the details that impact each water system and domestic well? So being a former project manager from my early years, I know that every project is a story unto itself. We're in danger of getting into kind of stereotyping or generalizations that can lead us astray at times. And so we have to always in the back of our mind remember that that's a solution set and it'll help with an estimate, but in the end, we don't want to pretend like we know exactly how that system's going to be solved, even if we're pretending like we do for the purpose of the needs analysis. And then any benefits and challenges to cost modeling software. Those always come with assumptions and potential error bars that we need to be aware of going into that. Next. Thank you. That's it. So I'm going to turn it over to the people that are going to be more interesting than me. Hopefully that sets up kind of what we're expecting today and helps shape the discussion later, and we look forward to definite participation. So, and Chad, get me out of here.
Maybe we have time for one question for Darren. Let me run a mic.
Well,
Why is the flux so large? Is it like
No, that's just systems that are coming in and out of compliance. So her question was, why is the flux so large of systems in and out of compliance? And it's, systems are always trying to stay in compliance, obviously, and they're trying to address that. Some of them don't take action until they're out of compliance, but it's a mix of factors. Some of it varies on the treatment type or the violation type that can be more transient. So if it's, there's all the scenarios. There's some of them that are right at that boundary and they bubble up and down based on maybe the seasonal rainfall and how well the well's producing, and has other inputs. There could be, if it's THMs, it could be whether it's summertime and they have high organic content of the water that's creating disinfection byproducts, and then they go to the winter and they don't, and they bounce in and out. There's lots and lots of reasons, but it's important to realize that it is a big flux rather than a small set that we're dealing with. I think that means we're really expanded quite a bit beyond what we would normally anticipate as a solution set. Yeah.
Maybe we'll hold the other questions for later on this afternoon.
Sure. Yeah, I think great.
So our next presenter is Eugene Luong. He's a drinking water treatment technical specialist for the Division of Drinking Water. He's based in our Richmond office. He's been with DDW since June of 1997, at first as a staff engineer and associate engineer in the Santa Clara district. And Eugene graduated from UCLA with a bachelor's and a master's degree in civil and environmental engineering. Thanks, Eugene.
Thank you, Chad. Good morning, everybody. So I'm here to kind of like set the stage for our discussion today. I'm going to provide background information and cost models used in regulatory development so that this is what we have available for a public water system, and we can look at how we can extend, maybe use some of those models or need to develop new ones for the really small water systems that we're talking about. For drinking water standards in the U.S., just to set the background, so the federal government sets up the Safe Drinking Water Act, the federal one. It's under U.S. EPA, so it sets the basic drinking water standards for all water systems across the country. And you can find information about it on the link on the website. For California, we are a primacy state, so U.S. EPA delegated the regulatory authority for regulating public water systems to our state. It's under the State Water Resources Board, under our program, the Division of Drinking Water Program. We moved over from the California Department of Public Health to the State Board in July 1st of 2014. And you can find more information about our program on the link. For water systems that are subject to Safe Drinking Water Act statutes and regulations, we broadly call those public water systems. So what is a public water system? It means that it serves at least 15 service connections or 25 peoples at least 60 days of the year. So all of these systems are subject to the Safe Drinking Water Act. And keep in mind that a public water system has nothing to do with ownership. A public water system could be public or privately owned. As long as you serve that many connections or populations, you are defined as a public water system. And community water systems are what we generally deal with the most. It is defined as a public water system that serves at least 15 service connection or 25 people regularly year-long residents. So when people live there, they get exposed to water the most, so that is a community water system. And most cities and everything that we deal with is a community water system. So for state and federal drinking water standards, there are two types that you need to think about. For drinking water standards, the federal government broadly sets the drinking water set the drinking water standards for majority of the contaminants, but there are some that's only state regulated because the federal government, we feel that they don't address the contaminant adequately. So for example, we have state-only drinking water regulations on MTBE, 123 TCP, and also for hexavalent chromium. So those are the two different levels. So for California, for us to retain primacy with the federal government, we must set drinking water standards that is at least as stringent as the federal government. So for water systems smaller than public water system, which Darren touched on, so I just want to define it here on the slide so as we have it available. For state small water systems, these are systems that is below a public water system. They're subject to regulations that is less stringent than a public water system. So there are some requirements, but it's substantially more relaxed compared to what a public water system is required to do. And this generally is serving systems that have more than 5 service connection, but up to 14 and less than 25 people year-round, and these are generally regulated by our county health departments. And then for domestic wells, these are for the really small systems now. These are for wells that's serving an individual private home or up to 4 homes, so 1 to 4 service connection. And for this type of system, they're not subject to any state regulation. They're only subject to maybe some local county requirements. So the top water quality challenges for groundwater systems in California, looking at our public water systems, the larger ones, as an indicator, the top 5 that I've listed here is bacteriological, nitrate, arsenic, uranium, and organic contaminants. So 1, 2, 3 TCP it's turning out to be quite a contaminant for us in Central Valley. There are quite a few systems that's detecting 1 to 3 TCP that needs to provide treatment. And for bacteriological, it's actually a well construction issues. As we dive into the smaller water system, the well may be in poor construction and subject to contamination from maybe a leaky septic tank or something that's around. So that's something that we actually have to deal with a lot more when you deal with the smaller water systems. So here's a quick summary of available technologies. What do we deal with for a larger water system? What is the best available technology that's been identified for treating all these contaminants? So I've excluded bacteriological, and then you have the 4 types: nitrate, arsenic, TCP, and uranium. So looking at this, the ones with the black X's is just the best available technology. This is specified in the regulation. But the ones with the red and an underline for most commonly used, that's what we actually see public water systems inputting it in. So for nitrate treatment, most systems actually try to drill a well, somehow get blending of sources to get away from treatment. But if they don't have a choice to treat, they get into this is the toolbox that they have available. Generally speaking, it's ion exchange, reverse osmosis, and electrodialysis. But we really do not have any electrodialysis treatment plant in the state of California. We only have some really small-scale reverse osmosis system, and then generally it's ion exchange, and the biggest issue is dealing with the residual from ion exchange treatment. For arsenic, again, there are multiple treatment options available. The most commonly used options are adsorptive media and coagulation filtration. And adsorptive media is actually one of the treatment techniques that's identified as most feasible for small water system. But in California, actually, we have a really poor performance from adsorptive media because of naturally high groundwater pH. So that actually creates an added level of complexity for us. For TCP, we only have one treatment technique, is GAC. So if you have to treat, that's the only choice you have. And then for uranium, there's a broad, again, multiple treatment options available, but the most commonly used one is for ion exchange. So now we shrink it down to the smaller water systems for point of use or point of entry treatment scale. You can see a lot of the more complicated treatment technology just falls off. The only treatment techniques typically available for home use, it will be reverse osmosis or single cartridges like adsorptive media for you to be able to use it. So again, I use similar to what I've indicated on the previous slide, but 2 things to identify. For the point of use and point of entry treatment, for nitrate, you can only use it pretty much typically for a point of use device, but the devices available in the market has very limited capability, and there's not a single device that's certified available to can operate above an influent concentration of 27 milligrams per liter, and for it to bring into drinking water standard. And then for adsorptive media, there's no certified device available. It doesn't mean it's not capable, but there's no certification standard for it. That's why we don't have certified devices available for TCP. So cost models. So I'm going to go back to, so I'm going to present here is a list of the kind of cost models that we've used historically for us to develop our drinking water regulations. It's kind of like a little trip down memory lane. So for nitrate, actually it was established so long ago, there was no cost model used. It was just established by the US Public Health Services that nitrate is a problem. So no US EPA cost model exists. And that's how we got our 10 milligrams per liter nitrate as an standard. For uranium, California actually established a standard before the EPA in 1989. Again, there's no records that I can find available for the cost models, but that's how it was established. So starting that, we have more information available starting around the year 2000. So for arsenic, that's one of the big regulations adopted by the federal government. And they actually put together a report on the technologies and costs for removal of arsenic from drinking water. The link on the slide is available, and you can click on it to actually draw the actual documents that was prepared by EPA. And for the California regulations, we actually developed our final statement of reasons that heavily use the EPA document. And you can find the reasoning justifications available by clicking on the link on the slide, and you'll be able to see the background document related to how we've gone through the cost and estimate for the cost for compliance in California. And then for 123 TCP, this is one of our most recent regulatory package. We actually use a new cost model that was developed by the federal government, is the WBS cost model for GAC, and then we will be able to use that to estimate our 123 TCP treatment costs. Again, the links provided on the slide, which you can click on later, will take you to the actual documents that we used and justification how we developed the cost for 123 TCP. So the WBS model actually stands for Work Breakdown Structure Cost. It's a pretty robust model that EPA developed. It covers systems from really small size of a population of 25 people up to 100,000. And it breaks it down into stepwise, different size groups, 7 different size groups. And it's available for some of the treatment technologies. So they have it available for granular activated carbon, packed tower aeration, multi-stage bubble aeration, and ion exchange and cation exchange treatment. So the link on the bottom of this slide will be able to take you to those models if you want to take a look at them. So for hexavalent chromium treatment, actually in that case, when we developed our previous MCL that's currently withdrawn, we based heavily on the treatment technique and treatment study that was done at the city of Glendale. And the links on the slide will be able to take you to those study reports on how they gathered the cost, and we use that information as part of our cost projection for compliance. And then for strong base anion exchange, in parallel, Water Research Foundation actually did some additional work, and they actually published a report, 4450, that goes into details of how they developed the ion exchange treatment model, and also they even have a calculator available for the larger treatment plants. So that's a summary that I've provided, all the different cost models that's readily available for regulatory development. But when we look at the smaller system scales, all these models kind of runs into limitations, especially for really small groundwater systems. This is just kind of like some comments and adjustments that we usually have to make when we do cost projections. The broad and because we're trying to do it on a statewide basis. So as Darren mentioned, every time that we look at sources over the MCL, we expect and we assume that we need to provide treatment. We don't look at any alternatives, we just say like they have to treat. So to create our cost compliance estimate. So all sources based on source water type assume to use the same treatment technique. So we just look at what's available and what's most similar to other systems have used in the past. So for example, for groundwater systems, for small system, we want to use something that's easy to operate, maybe a single pass use and toss type treatment system, so that they don't have to worry about regeneration or anything like that. And then for the larger water system, maybe they can handle a filtration plant. So that's kind of like the assumptions that we make. What's practical for them and what's reasonably that they can able to operate. So for the national cost models that's developed by US EPA and other, one of the key things that we've noticed is that California is just expensive. We have much higher labor costs, material costs, residual disposal costs, and all sorts of compliance costs. So if we use the national model, a lot of time we exclude those local factors that may not be adequately addressed. And for example, for arsenic treatment residuals, using the US EPA is simply ignored the residual disposal costs. So there was actually a supplemental report that was put together. It's like, in California, if we treat arsenic, this is the additional disposal cost that the national model never included. And then one more thing is for escalations. A lot of these models were done in the past, so like maybe in 1998. And then it's not uncommon for us to use the ENR construction cost indices for updating cost estimates. But we really live in the most expensive part of the country, and with really hot real estate markets, so everything just costs more. And the ENR index is just based on the 20 cities average. So maybe we actually make more issues when we use that adjustment, and we need to add a California factor to that. So statewide treatment cost estimates for public water systems. So this is just kind of like to give everybody background on how we generally deal with the public water systems level and not the small system, and maybe you can have an understanding of how we do it in the past. So for public water systems, first we look at a very clean water system inventory. So we know what type of water system they are, they're active, what type they are, and then get current information on the population served and service connections. and look at how many numbers of active sources they actually are in use. And then we look at the occurrence data. Based on all those active sources, how many of those sources will exceed the various proposed MCL levels? So we just don't look at one number. We look at the different numbers to see what's affordable. Like for arsenic, they actually look at 2, 4, 6, 8, and 10 parts per billion. And then for treatment techniques, we review the available treatment techniques that can achieve the proposed MCL level reliably, and then review available costs and different cost treatment models available, and then adapt and modify them to fit our needs. So the assumption for design flow, this is probably one of the trickiest things that we have to do. Because all of these are groundwater systems, there's a high chance the well is actually producing a lot more water than what we estimate. Because these are groundwater systems with no storage, so they actually have to put in a pretty big well for fire flow. So that can actually escalate the capital cost a lot because they need to put in a bigger treatment plant. But the reality is they may be using the plant very infrequently, so it's a very low utilization rate. So that actually drives up the cost for capital, and it actually may impact the performance of the treatment plant too. When you oversize a treatment plant, it doesn't work really well. But the basic cost assumption that we do, the design flow assumptions we do, is first based on population, and then we assume that each person's use about 150 gallons per capita day. And that's actually, we've looked at it based on indoor use, looking at 15 numbers. We actually, overall in our country, we're dropping down to around 130 GPCD. So this is a pretty conservative estimate. And then we assume a peaking factor of 1.5. So because everybody potentially use the water at the same time, like in the morning or coming home in the evening. And then based on service connection base, if we don't have the information on population, we just look at the number of service connections they have, assume there's 3.3 people per household, and then using the same factor to generate a number. But now, when we come back for a check and look at it later, which I will show you in our case studies, is we actually look at the design flow. The design flow for most of the system that actually come in, as I mentioned, they're using the actual well production rate. So a lot of times it's substantially higher because of fire flow. So treatment options, again, looking at, I'm going to show kind of like a little flow path available. The best available technologies are BATs. We're just talking about technologies that have been proven effective for water systems to use. It's not proven for all sources, but generally this is what, at the time of regulations development, these are the best available technology. After we adopt it, a lot of times when we create the demand, there's actually some more innovative technology that comes in that's not considered BAT. So in our state, we actually call those conditionally accepted technology. And then for small water systems, the federal government actually has something called Small System Compliance Technologies, or SSCTs. So they recognize that small water system, it would be too difficult for them to operate these treatment plants. They actually specify which are the ones that's intended for small system that they're capable of operating. And one of the key things that I want to mention is when you look at cost, it is not just capital cost, it is really the long game. It's the operations and maintenance cost that's needed to make sure the treatment system's working properly. One of the key things for a lot of these groundwater systems is they should have just been operating a well before, very simple, or maybe as a minimum just chlorination. It doesn't really require a lot of operator skills. But the certified treatment operator cost and the increased testing actually escalates the operation cost for these small systems quite a bit. And then waste disposal costs. We don't want people to treat and just dump things illegally. So you just concentrate it of waste and then you illegally dump it. It kind of defeats the whole purpose. So we really need to responsibly determine and include the cost for waste disposal for both liquids and solids for the treatment residuals. And for treatment options, when we talk about it on larger case, on public water system scale, our preferred is centralized treatment. Just treat all the water coming from a well because that's the easiest for a large water system. They just put in one treatment plant, they monitor how well it works, and many treatment they just need to do it at one place. So that's the preferred method. But for some of the smaller water system, because they use so much water that's outdoor use and they have a really small cost base, we look into other options like point of entry treatment and point of use treatment. And briefly, point of entry treatment means that you're just treating the water entering your house. So you're probably putting a filter in your garage. So all your indoor use will be treated, but all your water used for outdoor irrigation is not treated, and you probably need to run a line to your backyard so your sprinkler is not tapping off your kitchen sink. And then for point of use treatment, this is something that you just put under your kitchen sink, and then it's only treating a very small stream of water. And this could be useful for something like a small community or a non-transient, non-community system, like a business that you just put in the break room, so all the water that's used where people actually internally consume the water will be treated. So here's kind of like a little decision tree that we have together. This is just an example, one of many. This is for arsenic treatment options, and they have different group types. Next. So looking from the top, it's actually our favorite option and preferred option is the no treatment option. So for a water system just looking in itself, the best option for them is maybe help them get a new well, drill a new well that meets the drinking water standards so they don't have to deal with the long-term treatment. That's the preferred. And if they have ability to get alternative sources, like maybe buying watering from a neighboring system to supplement what they've lost and the other system has enough water to sell them, that's an option. And then last but not least, if the two wells, if they blend the water together and can meet standards, maybe just help them put a pipeline together and storage tank so they can blend the water to compliance. What's not mentioned in this option is actually consolidation. In the past, we really don't look at one system taking over the other, but I think in our current situation that a lot of times consolidation is probably the most preferred option because you really eliminate one system and then make it much easier and lower cost for the long-term O&M. Next. So for treatment options, for systems that may be just too far to consolidate, the options they have, like I said, in the BAT, there are 6 different options, but the reality in the marketplace, there's 2 types of treatment, either using adsorptive media or oxidation, coagulation, filtration. Those are the 2 treatment options that's commonly used for arsenic treatment. And then finally, for interim solutions and for non-public water system, what we're talking about. So point of use and point of entry devices, those are the options that we can consider. And these we even use as what we call interim solutions because the regulations, the state law limits our use of point of use to every 3 years. And at the end of the 3 years, we evaluate if there's a better option that may have come about that centralized treatment, we'll take it. If not, we'll just renew and use POU or MPOE again. And then vending machines has often come up as a potential options, maybe like as community kiosk for people to come fill water to like just treat the water. But one of the requirements is that for any vending machines, it's dual regulated. It's regulated by the Department of Public Health, Food and Drug Branch. So I just put it up there just as a reminder that if we go down that path, we need to make sure that we have both addressed it through the drinking water program and also through the Food and Drug Branch. So here's a slide for the arsenic small water system compliance technology put together by the EPA. I think there's some really small prints here, so I'm not going to read it to you, but you can see like some technologies is meant for big systems, some is like they just exclude it, it's not for small system. But when you have time, when you look at the slides later, it really talks about even if you use a point of use device for reverse osmosis, because it is not the most water efficient treatment technique. So it says if you have a system has a water quantity problem, a point of use arrow may not be the best choice because it is wasting a lot of water to make your drinking water. So that's something to take a look at this particular slide, but I'll let you guys study that later. So here's a good comparison for all of you to look at the comparison between centralized treatment and point of use device. I think the key thing for point of use for you to be able to administer it and for it to work, I'm not going to read the slide to you. The most important thing for point of use device is not just set it and forget it. Is you really need to go back and ongoing maintenance to change out the filters and cartridges to make sure it's working properly. So it is the critical, the maintenance and monitoring to make sure it's working properly. The routine maintenance is required to ensure effectiveness, depending on type of unit you use. And then the ongoing maintenance work could potentially be contracted out to maybe some of the supplier to do it to make it a bit easier, but that's a key cost for the use of POU, POE, is to enter people's homes and be able to maintain these units regularly. So just for pictures to show you, on the left side, this is the type of kind of like a big, maybe a softener type device or cylinder that you can install in the garage for treating point of entry. And then on the right is a point of use treatment device available for arsenic. And that's something that you can actually connect to the aerator, take off the aerator from a kitchen sink and then screw this on and be able to use it for arsenic filter. So the biggest issue with this one little device that I love is it doesn't have a flow meter, so you never know how much water you've treated and when to change it out. But otherwise, it's a fantastic design. It's very simple to implement, but it lacks a warning to let you know that the filter is exhausted. It's time to change it out. And then these are some other pictures available. These are the typical reverse osmosis POU device. It takes up half your kitchen sink under it. It becomes really difficult when you implement into people's homes because different types of plumbing, maybe it's on the verge of breaking and you have to go in and cut into both the drinking water line and also the waste line, and drill a hole in their kitchen counter to be able to put in the separate tap. So this is the type of our device we're talking about, but it is actually a lot of liability and difficulty when you install these devices into a customer's home. So I'm going to do 2 quick case studies, just kind of like comparing all the models we have shown earlier and compare it of what we know, just the capital cost. So there's 2 water systems that I'm going to use as a case study. One is Alpal Community Service District is in Tulare County. It's a small system with 392 service connections, serving a population of about 1,000 people with 2 active wells. And then the water system is Bridgeport PUD in Mono County. Again, a similar size water system, 258 service connection with 850 population. So looking at how we normally proceed, so this is just for comparing the capital costs using the models. This is using the EPA model, but we have escalated the cost to $2018, so it's for easier comparison. So based on the population and service connection, you can tell that the treatment plant that using the model will produce a relatively low number because we assume that the well is running all the time at 150 gallons per capita a day. But if you look at the actual design flow that's needed for a system based on the well production capacity, the number is much higher. So based on the US EPA model, based on the real flow, the estimated cost is about $826,000 for this particular treatment plant to put in an arsenic adsorptive treatment plant. So the system actually gone out for bids. So there were actually 3 bids that came in. Roughly, the average of the 3 bids was around $3.3 million. The standard deviation of the cost was $239,000, so around 7% deviation. So it really showed, and the winning bid was around $3.1 million. So with the really small deviation, so this was pretty competitive, and the winning bid was pretty close. All the bids were pretty close. But if you just look at it on the surface, the winning bid is substantially higher. But upon closer inspection, you notice that actually the true project that includes some solar arrays and then some of the parts that's not included in the construction cost estimate done by the EPA. I have a slide later to explain what's included and what's excluded. So we did a rough attempt to isolate the project cost, and then after adjusting it, looking at it, the cost estimate would be about $1.9 million. So it's still around 2.3 times higher than the EPA estimated model. And then here's case study number 2. This is for Bridgeport PUD. So again, we did the estimates based on service connection and population, and you can tell for the true flow of the well is 9.36 MGD. So again, the cost is substantially higher than just based on the population, and the estimated cost is around $888,000. And then for this project, it's actually they have changed gear midstream. So actually, the original cost of the project for them to be constructed was around $1.4 million. So that's only 1.6 times the US EPA model. However, they used adsorptive media, and then they tried to run it, and the media was breaking through way too early. So they actually changed the plan, and they want to modify it to a coagulation filtration plant because they just can't afford to operate the adsorptive media. So the equipment from the adsorptive media system was salvaged, and then really we can't directly compare the cost. But the final cost of the project, our estimate right now is $2.7 million, and then the original estimate was $888,000. So the general comments, high-level comments and studies in US EPA model. So based on the 2 that I've shown so far, it's just really limited sample size to draw any conclusion. But the cost model seems to underestimate actual cost. The US EPA construction cost estimate include only housing, electrical equipment, instrumentation, pipes, valves, labor, steel, concrete, manufactured equipment and excavation and site work. However, their estimates don't include special site work, general contractor overhead and profit, engineering, land, legal, fiscal, admin work, and interest during construction. And all of these is actually a lot of costs that's being ignored. So the operations and maintenance and O&M costs, we were not able to compare it because one of the treatment plants is not yet running. But overall, it's sort of the media for arsenic are underperforming in California due to the really high natural pH of our water of greater than 8. So that makes it extra challenging for us for arsenic treatment. So the big picture now, taking a step back, the big challenge for us, the challenges and total costs for long-term success. We're really looking at how do we set up the system for success. The operator costs, the labor is really high. We need to recognize this during startup, during optimization and maintaining water treatment facilities. We cannot just build it and walk away. There is an ongoing labor cost there. And generally, we have a lack of qualified operators in the state as well. To operate these centralized treatment plants. Even though if we build it, we have difficulty in finding enough qualified operators to do it. And there's also lack of qualified subcontracts to perform the work for point of use and point of entry. There's some interest, but there's not enough qualified personnel to roll out there and to install and maintain all of these point of use and point of entry devices properly. And small water systems generally lack someone in a water quality manager role. So they just really look at pay the bill and whatever we tell them to monitor, but it's always very reactive. So there's no one to monitor the overall, take a big picture of the treatment performance, initiate preventative maintenance, and ensure ongoing compliance. And then last but not least, and water system also lack any long-term asset management planning and resources. So they can barely pay paycheck to just pay the minimum bill, and they're not setting aside funds for replacement of treatment plants and replacing aging distribution pipes and wells. So all of these goes into challenges for all our projects. So to wrap up my presentation, I want to acknowledge Dr. Richard Sakarji for helping me put together all the information that I've presented here today, and I'm open to questions.
One question in the interest of time.
Okay.
All of this factors into the best water treatment system. So how do you factor in this into your model?
So for our compliance costs, generally we assume an average condition in the state, maybe assume that the pH is 7, we just need to adjust that up to 8. So just kind of like generalize it to be able to estimate a treatment cost for, but we really have not done afterwards to do a forensic to see how close they are. This is, I think, for me, it's the first time that I'm comparing what was actually done to what was predicted.
If you don't mind, I just have a follow-up question. Because when you say best water treatment system, I mean, it really depends on the well that you're inspecting, because their pH, it could be their contaminants level. I mean, like if you put an RO system, yeah, it removes a lot of contaminants, but if they have a low pH or they have a low well yield, you wouldn't want to install a RO system. So I
completely agree. It is a very, very challenging question, and that's why I think we're having this workshop to see how we can and look at different types of system, maybe looking at areas that is very low water yield, and maybe able to assign some treatment costs to that region, and then maybe having some area that is not as short on water, and then maybe they can use RO. I don't know. I think we are open for the discussion today.
I'd just like to add, if you have questions, additional questions, Mary will provide you with a comment card, and we will collect those and speak or address them later. Thanks.
Thank you for your question. I mean, I think it really highlights how right now we're dealing with individual systems and doing pilot studies, but that information doesn't translate into a more global or statewide effort like we're trying to talk about today. So thanks for your question. I really appreciate the comments by Eugene. Our next presenter is Lucio Orea. Oriana, sorry, Lucio. Lucio is a registered civil engineer. He works currently for the Division of Financial Assistance for the State Water Resources Control Board, and before that at the Central Valley Regional Board.
Morning, everyone. Again, my name is Lucio Oriana, and I'm a senior engineering specialist with the Division of Financial Assistance Office of Sustainable Water Solutions. In today's presentation, I will focus on the availability of capital and operation and maintenance costs that we receive through the division through our funded projects. I'd first like to give a quick overview of the program, including the types of drinking water projects and water systems that we fund, and the types of funding that is available. I'll then talk about the specific documents and cost information we have available, and finish off with some of the factors that could affect some of the costs that we are seeing. The Division of Financial Assistance, also known as DFA, administers the implementation of the State Water Board's various financial assistance programs, including low-interest loans, principal forgiveness, and grant funding for the planning and construction of water system improvement projects, emergency drinking water needs, and as well as technical assistance. Within Within DFA is the Office of Sustainable Water Solutions. The office was created to promote permanent and sustainable drinking water and wastewater treatment solutions. The office focuses on addressing technical and financial assistance needs, particularly for small disadvantaged systems. Funding is provided for the planning, design, and construction of drinking water infrastructure projects, which includes treatment systems, distribution systems, interconnections, consolidations, water sources, water meters, as well as water storage tanks. Some of the eligible applicants include publicly owned water systems, such as your counties, cities, and districts, privately owned water systems, mutual water companies, as well as nonprofit, non-community water systems, public school districts. For planning projects, the eligible costs include the preparation of feasibility studies and project reports, engineering and design documents, environmental documents, drilling of test wells, pilot studies, the completion of technical, managerial, and financial assessments, along with the supporting documents, as well as consolidation agreements. For construction projects, eligible costs include the purchase and installation of the treatment facilities, drilling and equipping of production wells, consolidation project components, replacement of pipelines and water mains, pump stations, interties, storage tanks, as well as consolidations costs such as connection fees or additional sources to meet the additional demand. If we go back to the other slide, please note that the ongoing operation and maintenance costs are not eligible project costs. Technical assistance is also available to small disadvantaged communities through third-party providers for services such as completing funding applications, any legal assistance, completion of income surveys, assistance with technical, managerial, and financial assessments, rate studies, and as well as board and/or operator training for the water system. Early on in the planning phase, recipients will prepare a preliminary engineering report or feasibility study where they analyze all available alternatives and recommend the best option or combination of options to address the water quality issues or the water system deficiencies. These reports typically include water treatment options, system improvements, and an analysis of consolidation with nearby public water systems. For each alternative, estimated capital, operation and maintenance costs, as well as life cycle costs are provided to help the water system, Division of Drinking Water staff, and DFA staff to coordinate on the most sustainable solution. Applicants also prepare a final engineering report that includes details on the selection of the preferred alternative and proposed construction project. The report includes information such as the basis of design, conceptual design, and the engineer's preliminary opinion of probable construction costs for the selected construction project. These cost estimates are only reflective of the specific project at the time the estimate was developed and could be different than the costs we may see when the construction project is complete. Here's an example, it's probably a little small, but of an engineer's estimate of probable costs that may be submitted, which provides a breakdown of items necessary for the selected construction project and could include information such as estimated quantities and unit costs for specific project items. The reports that are developed are typically submitted in PDF files that are saved to the individual project in our tracking database. So the estimated capital and O&M costs are only accessible by manually going into each project, looking to see if the report is attached, and then search it through the report for the needed information. As you can see here, maybe a little bit too small, there are a number of documents that could be submitted for any of our funded projects. Here are some examples of estimated capital costs for arsenic projects we have received for some of our planning and construction projects. As you can see, there are costs that vary for different size water systems. One of the common things water systems evaluate during planning projects is the need to also address other system deficiencies. These deficiencies can range from additional water sources, replacement of aging infrastructure, or fire protection. Addressing other system deficiencies leads to additional design and environmental costs for a larger project, which is reflective in the higher project costs. So if we wanted to see the capital cost data that addresses a specific water quality issue, we would need to search through the submitted reports to see if a detailed cost breakdown is available, and then go through each line item to determine the specific treatment cost. Project costs are reimbursed when a recipient submits a reimbursement request form with supporting documentation such as invoices for the incurred project costs. The invoices provide actual costs for specific project tasks, such as drilling of a test well, any pilot studies conducted, as well as the consulting rates. The submitted reimbursement request and supporting documentation is submitted by hard copy to our disbursements unit and is filed in project folders. They are not available electronically in the project database. What does get uploaded to the individual project in the database is a copy of the approved disbursement request form, which does include a summary of the amount claimed for payment for specific budget line items for the project. For construction projects, we again see a final engineering report for the selected construction project, which may or may not have been completed with planning funding. We see similar information I mentioned in the planning projects, along with the final plans and specifications for the project. Similar to the planning projects, the report and engineer's detailed opinion of probable costs is submitted as part of the construction application and uploaded to the individual project in our database. So those cost information will again need to be accessed manually. Construction agreements are initially issued with planning and design allowances for reimbursement of soft costs upon completion of upon execution of the agreement. Construction allowances and associated disbursements are not available until after the agreement has been amended to incorporate the final budget approval form. The FBA form is completed and submitted along with supporting documents when the recipient has completed the formal bidding process. Some of the attachments include a tabulation of all bids or proposals received, the copy of the bids and proposals selected, and a final breakdown of construction costs. The FBA form and supporting documents are submitted electronically and attached to the individual project in our database. Reimbursement requests with supporting documentation of actual construction costs and consulting rates are also submitted by hard copy and filed in our project folders. It's important to note that the cost data we receive is only reflective of the specific project at the time the project was constructed and may differ from costs that we may see in future funded projects. The Emergency Drinking Water Program provides interim drinking water needs to water systems due to drought, contamination, or other eligible emergencies. For funded interim projects, the estimates and actual costs of bottled and/or hauled water are provided by the vendors or water suppliers. The cost data is available electronically or by hard copy in the respective project files. The Drinking Water for Schools program provides funding to improve the access and quality of drinking water in public schools. Estimated and actual point of use cost data could be available for labor, materials, monitoring, and installation costs for point of use devices in schools. Cost data for this program is also available electronically in the project files. Part of the planning and construction applications is the financial package, which requires the submittal of audited financial statements for the water system. The audited financials typically contain yearly operating and maintenance expenses. For grant-funded construction projects, audited financials are not required to be submitted once the project is complete. There are some loan-funded construction projects that do require water systems to submit their audited financial statements after the project is complete, and those statements could be available electronically in our project database. Some of the factors that could affect the costs of our funded projects include the proximity of the water system or community to nearest public water systems for consolidation projects, the location and accessibility of the water system or community, the demand for specific trades, such as drilling a well during a drought, no or single bidder on construction projects, the regulatory review of a project, such as the Division of State Architects review for school water system projects, and compliance with federal cross-cutters such as American Iron and Steel, Davis-Bacon, and Disadvantaged Business Enterprise. That concludes my presentation. I believe maybe we have time for one or two questions, if they're available.
We have a question out there. Sure.
When you receive a request, when you receive a request, do you do your own cost estimate to compare with the cost estimate they've submitted?
You mean for the reimbursement requests? So those are the actual costs. So when they submit the reimbursement request, they submit the actual invoices for the incurred costs for the specific item. And so those are the costs that we receive are those actual costs for any of the tasks associated with the project.
And so do you have your own cost estimation to compare with the actual costs you receive?
We don't have our own cost estimation, but what we could compare it to would be maybe some of the estimated costs from the planning projects that we funded. And then if that project comes back for construction funding, we can perhaps compare those costs from the estimated and then to the actual cost of the completed project.
And so when you're doing the estimated costs and the planning, are you doing that? Or?
No, those are the engineering consultants that are hired by the water system, and they're the ones that complete the engineering reports. They put together the cost estimates and they submit them to our project managers, and there's coordination between the Division of Drinking Water staff as well.
So do you have your own way of assessing whether that's ballpark or?
That's a good question. I mean, we have costs that we can maybe take a look at for if certain projects are doing the same treatment type for a specific analyte, or whether they're in certain areas within the state. Perhaps we can take a look at some of that cost data to see how they compare to one another.
I see. All right, thank you.
Sure.
Thanks, Lucio. So our next presenter is Mr. Matthew Newman. He's a joint founder of the Blue Sky Consulting Group. Mr. Newman specializes in quantitative analysis of state and local fiscal, economic, and public policy issues. Mr. Newman was the founding executive director of the California Institute for County Government, a nonpartisan public policy research organization supported by the California State Association of Counties and the California State University System. Mr. Newman earned his bachelor's degree from the University of California at Los Angeles and holds a Master of Public Policy from Harvard University's Kennedy School of Government. Mr. Newman.
Thank you. Good morning, everyone. So I'm Matthew Newman from the Blue Sky Consulting Group. We were engaged by the Water Foundation back in 2017 to try to kind of take a stab at this whole needs assessment idea, which the Water Board's now engaged in this much larger process for. That project was really more of a back of the envelope effort to try to provide some information to stakeholders and then ultimately to lawmakers who were trying to just get a sense of what the order of magnitude was for these kinds of costs. The time frame that we had was quite abbreviated, and the budget, unlike the $3 million that the water board has, if you took a couple zeros off that, you get pretty close to what we had. So what we were really trying to do was just, under conditions of uncertainty, try to put an estimate on what the costs were for providing safe drinking water to Californians. I think the, do I have the ability to change my slides? No, okay. All right. The origins of this project are important for interpreting the results of our analysis, which I'll show you a little later on. And they were, as I said, a group of stakeholders got together and were convened by the Water Foundation to try to come up with an agreement for a funding package that would have agriculture interests pay some of the costs of treating contaminated groundwater, and also come up with some additional funding sources to provide treatment options for non-nitrate contaminants that weren't necessarily due to fertilizer. So those stakeholders had very specific interests in kind of what the package was supposed to look like, and those interests really defined what the boundaries of our analysis were. So we can go on to the next slide. These things really actually matter, I think, quite a bit more than the kind of technical cost considerations, which I think consume most of the effort, and I think those are extremely important as well. But I think we don't spend enough time thinking about how the boundaries of the analysis influence the cost. So, for example, who are we talking about? Earlier, Darren talked about focusing on small communities. That's what we did as well. We looked at communities under 100,000 people. But which communities do you focus on? Is it just economically disadvantaged communities? Is it all communities? Which contaminants are you looking at? We were focused on nitrate and other contaminants, but we wanted to look at the costs for nitrate contamination, particularly because of the agriculture interests that were part of the process. So those things really shape what the analysis looks like. And we also have to look at things like, what's the time period we're talking about? Are we talking about forever, or the next 15 years, or the next 20 years? So these things all have a really big impact on what the final results of the analysis might look like. We can go on to the next slide. So ultimately, the analysis that we did was we built a model to estimate costs that looked at nitrate contamination, but also contaminants, other kinds of contaminants from arsenic and hexavalent chromium and the other ones listed on the slide. Basically all the ones that the water board had an MCL level for, plus hexavalent chromium, which there used to be an MCL for, but is being revised, as you guys probably know. We decided to look only at communities up to 100,000 people. There's obviously some disadvantaged people in larger communities, and there's even some larger communities that might struggle to pay to stay in compliance, but that was kind of the boundary that we drew based on the stakeholders that were guiding our process. Because of the interest in getting agriculture to pay for some of the costs of nitrate contamination, we looked separately at communities that were only affected by nitrate contamination, also at communities that were affected by nitrate and other contaminants, and then finally at communities that were affected by contaminants other than nitrates. For communities that were affected by other contaminants, other non-nitrate contaminants, we looked at just low-income communities because the idea was to means test, and if a community was not low-income, the assumption was they can afford to treat their own water. We were trying to figure out the cost for treating just the low-income communities. We can go to the next slide. Actually, we can go one more, sorry. The way we identified community or systems to include was we did this separately for water systems subject to state regulation, and then the small systems and domestic wells separately, because we had different information about which of those communities were subject to contamination. For the community water systems, we know about the violations, as we've talked about already today. So we looked for communities that had multiple violations, that is 2 or more violations, over this 5-year period from 2012 to 2017. Again, the idea was if a community has a single violation, it's likely that that community has, that violation could be temporary, as Darren was saying before. They might just have something that they can address relatively easily, and it's not necessarily an indication of an ongoing problem. And so in order to get a sense of which communities were more in need of help, that is those that are having repeated problems, we looked just at those communities with multiple violations. As I said, communities up to 100,000 people. And then we defined low-income communities as those communities with a median household income across the whole community that was 80% of the statewide median. Now, obviously, there's lots of value judgments that are made along the way in this kind of approach, and I think, as the Water Board goes through its process, I think it's very important to be very transparent about what these assumptions are, about which kind of communities are included, why those communities were selected, and also to present the results perhaps in a few different ways. If you only look at this kind of community, what do the results look like? If you look at a broader set of communities, what do the results look like? And maybe if you look at everyone, what do the results look like? And you have to be, I think, careful when you do this, because you could say, well, here's the cost for everyone. We're not making any judgments about who should bear those costs. That results in an extremely large number, a cost number, which might stall efforts to get a funding source and progress. So I think it's important to kind of think about the communities we really care about, and not just spend time on the technical modeling issues about cost and interest rates and how we estimate O&M costs and all those other things that are also very important, but to kind of keep focused on the big picture of what the goal for all this is. Okay, I think we can go on to the next slide. For each system that we looked at, we estimated treatment costs using the approach that was discredited by my panelist here just a minute ago, which was these EPA models, which is the best data that we had at the time, but that now appears like it was perhaps too low, at least based on these 2 examples. But that was the best data that we had at the time. So we looked at that treatment cost, the treatment cost estimates that the Water Board had. Those are organized by system size. So for very small systems, there's one kind of estimate, and as the systems get bigger, there's economies of scale, and the costs aren't quite as high per connection. And so we looked at the cost and attempted to size them to the specific communities that had multiple violations that were included in the set that we were analyzing. The one kind of exception to that was that for the largest category that we had data for was systems that serve up to 33,000 people. We were looking at communities up to 100,000 people, and we decided that rather than assuming that you would need 3 times the 33,000 system treatment cost, probably it was the case that that system had a single well that was in violation and wouldn't necessarily need to install a whole new treatment infrastructure for all of its water supply. So for systems that were larger than 33,000 people, we used the costs for systems up to 33,000 people, basically assuming that around a third of their capacity would need to be addressed through some kind of new treatment infrastructure. This isn't quite right. It says capital costs were amortized over 30 years at 4%. That's where we started. As I said, the stakeholders that were driving this process, we were trying to help them. They later decided that a fee on nitrate contamination, they didn't want to commit to one that would go for 30 years. They were willing to commit to 15 years. So we actually revised the estimates to do capital and O&M costs over 15 years. So the results at the end are based on a 15-year time horizon. Now, obviously, if you're paying off your capital costs over a period that's half as long, then the annual costs are higher. And so that's why I'm saying that the time period, that's one of the reasons why the time period for your analysis can really matter a lot. Finally, we tried as best we could to be very comprehensive and include all the kinds of costs that a community might face if it were going through this process of installing a treatment type. So we looked at technical assistance and planning costs, which we estimated at 15% of capital costs. And we also figured that the State Water Board would have some costs to administer some kind of new funding source. which we estimated at 5%. Now, as you've probably gathered from this discussion, what we didn't do was look at the cost for consolidation. That's a preferred method in many, many communities, but for purposes of what we kind of thought of as a back of the envelope estimate at the time, or establishing an order of magnitude, we didn't have the ability to identify what the capital costs would be for, which communities were suitable for consolidation, and what the cost for that would be. So that was not one of the treatment options that we were able to look at. Finally, we looked at the cost for emergency water just for the smallest communities, those up to 1,000 people. Basically, we figured once you've done the well testing, you've determined that there's a problem, we are obligated to provide some kind of safe drinking water for those people. And so we looked at whether bottled water would be cheaper or a point of use device, but it turns out that installing a point of use device is less expensive than bottled water if you assume it takes a few years for a capital project to be completed before you can provide safe drinking water through the water system. So we included those costs as well. Okay, on to the next slide. Now, as I said, the process of identifying who is subject to contaminated groundwater is different for those people that are not served by a water system that is subject to state regulation, where there's regular well testing and so on. We don't have the violations for someone if we don't know if your domestic well is in violation or if your water system that has 5 connections is in violation. There's not really any data on that. So we needed to come up with a new approach for figuring out how big is this population and what are the costs for serving this population. I think this is probably also one of the biggest areas of uncertainty for the current needs assessment effort, because there really just is very limited data about who is subject to contamination for these very small systems. The way we did this depended on the kind of violation or the kind of contamination that we thought the community was subject to. The 2016 CV SALT study, which you guys may be familiar with, looked at the costs of addressing contamination from nitrates just in the Central Valley, but they did provide an estimate of the domestic well users that were subject to nitrate contamination, in addition to looking at water systems more broadly. And so we were able to use their approach to estimate the domestic well users subject to nitrate contamination statewide with, I think, what is a little bit of a crude method, but was also the best and only method available to us, which was that we looked at the ratio of water systems with violations to domestic well users with violations in those communities. And we said if that same relationship holds statewide, then we can extrapolate up to the whole state and figure out an estimate or an order of magnitude of how many domestic well users are subject to nitrate contamination. So then we looked at the rest of the state that wasn't covered by the CV SALT study, what were the nitrate violations in those communities, and then applying the same ratio, estimated the number of domestic well users who were subject to nitrate contamination. Next slide, please. Now, for other contaminants, we had a different way to go about that. We had some data from Cal EnviroScreen, which compiled the available well testing data from all over the state, which is quite limited, but nevertheless was the best that was available. And they made, basically for the whole state, you're able to take that data, exclude population areas that are served by a public water system, and then you're left with the rest of the state, which is the area served by domestic wells or state small systems. And then those areas can be divided up into 6 square mile, that is 6 miles on a side, 36 square miles townships, which are quite big areas, but that was the kind of level of analysis that was available to us. And then that data takes the average well readings from that entire area and then applies or compares that average to the MCL to determine if that particular township has water that's exceeding the MCL level. Now, as I said, those are big areas, and it's very possible that you'd have a few wells that are in violation in one corner of one of those townships, and most of the people living in the rest of it would not be subject to contamination. So you could have a system where you're underestimating, or whether you're overestimating the amount of population subject to contamination. Conversely, this takes the average, and it's possible that there's a couple of wells that are serving the bulk of the population in that area that are really a problem, but when you take the average across all the wells in that area, you end up with a result that's below the MCL and doesn't make it look like that's in violation. Nevertheless, this was the best and only data available, so we used that to identify the townships that had contaminated groundwater compared to the MCL based on the average reading. And then we further said, because these are the communities that are subject to non-nitrate contamination, which of those are low income, again defined as 80% of the median income or less. And then we counted up the people that live in all of those townships, which we had identified as being subject to contamination. So the next slide, please. So then what we did was we had the number of people in these communities, and then we just estimated costs on a per capita basis. For many of these communities, they're served by a small system, or they might be adjacent to a system that they could connect to through consolidation. But for purposes of coming up with a kind of order of magnitude estimate, we estimated a per capita cost for all of these people based on installing a point of use device. We were concerned about the issue that was raised earlier, that these devices need regular maintenance, so we didn't just estimate the cost for installing the system, we estimated the annual cost for an installation and maintenance contract with a commercial provider so that someone would come back periodically to make sure the filters were changed and the equipment was operating properly. So we had an estimated cost for a point of use device for all of the households in these regions we had identified. We also tried to estimate costs for program management, and we assumed there'd be well testing costs, which would also be quite significant because there's a large number of wells, and so we estimated those costs as well. And then lastly, we assumed that some number of people would not be suitable to have a point of use device. They wouldn't want to have their well tested. They'd have pipes that were too old in their house for whatever reason. Those people would more or less indefinitely need to be served with a bottled water solution. And then finally, we assumed some ongoing maintenance or operations costs for the State Water Board at about 5% of the program costs. So next slide, please. So here's the numbers that we came up with. As I said, these are very specific to the unique boundaries of the analysis that we looked at. Just systems with multiple violations, just systems that were identified, or just domestic well users that were identified through this somewhat imprecise process of using the CalEnviroscreen data, and then only covering a 15-year time horizon, so all the capital costs amortized over 15 years. So what you can see here is we divided the cost up into annualized one-time costs. That's the set of columns on the left there. And we looked at public water systems and small systems and domestic wells separately. We identified the costs for systems with nitrate contamination, nitrate with co-contaminants, other contaminants, and then the total for all the systems. Did the same thing for the domestic wells. So that's the capital costs, assuming we finance them for 15 years at 4%. The next column is the ongoing annual costs. These are perhaps the most important because, as was pointed out earlier, there's really not a funding source for many of these systems or individuals to pay these ongoing costs. And as you can see, they're even more significant than the annualized capital costs. We estimated administration and technical assistance and emergency water costs, again, trying to be very comprehensive and look at all the costs that these users or systems would face. And so those end up being another 8.8, these are all in millions, by the way, so 38.16 million for the annualized one-time cost, 92.6 million for the O&M costs, 8.8 million for the technical assistance and emergency water, and then our total estimate was almost $140 million a year. Again, to treat the systems that we identified, all users or systems subject to nitrate contamination and low-income communities and systems subject to other contaminants over this 15-year period. So next slide, please. So I think the conclusion here is that the cost modeling is not just a technical task. It's obviously very important, and if the treatment costs are, as we learned today, possibly twice as much for some systems as we might have thought they were, then that obviously would have a big impact on the results. But there's a lot more to it than that. Most importantly, who are we trying to treat water for, and where do those people live, and which people are we talking about? That really matters perhaps even more. There's always going to be data limitations. Even with a $3 million budget, the Water Board will find that they just don't know for sure the costs for every system or exactly every user in the state that is subject to contaminated groundwater. And so assumptions will have to be made about how to address that, and that should not get in the way of coming up with an estimate. There's ways to try to be precise, to do some sensitivity analysis to see how important those assumptions are to your analysis. But we shouldn't let the perfect be the enemy of the good and not be able to come up with some estimates so we can get to the next step of actually addressing this problem. And to do that, of course, we need to know how big the problem is. So with that, I think there's a couple minutes for questions.
Yeah, we're gonna camp out a little bit, take a few more minutes for questions because I understand you may be leaving around lunchtime, so we want to make sure that if folks have questions for Matthew, sorry.
Yeah, either way, thank you.
They can ask them now. So, sir. Yeah.
What is that? Do you have a breakdown in each category on that error bar? Because, I mean, obviously there are a lot of variables. You did a good job of explaining all of that, but curious if you have an error bar and it's specific to category.
The short answer is no, we don't have a precise, it's 140 million plus or minus, 9 million. I can't tell you that. What I can say is there's a substantial amount of uncertainty associated with these estimates. As I said, it sounds like the costs from the Water Board and EPA models might be too low, although I think it's possible that in some cases the systems are less expensive to treat than we imagined, so is the average about right maybe? We don't know what we assumed treatment costs or installing new treatment equipment. Perhaps consolidation over the long run ends up being a cheaper alternative. So there's all these elements of uncertainty. The way we try to build a model like this is to include as many individual parameters, if you will, as we can, and so that the model is not as reliant on any one of those as it would be if there were a smaller number of them. So some of them might be too high and some of them might be too low, and we hope that on average the result is about right. But whether that's the right order, I think that is probably the right order of magnitude. Whether it's 10 million or 30 million off, I really couldn't say.
Thanks, Matthew. If you could have done one more layer deep on your analysis, what would you have done?
I think there's two things, actually, if I could offer two things. One is, on the domestic wells, we really had these what amount to very, very large geographic areas with very sparse well testing results in them. And so there's not a ton of people in each of these 6-mile townships because they're basically rural areas not served by a public water system. But that is the place where there was the most uncertainty as far as the data is concerned about who's affected and what kind of groundwater contamination they're subject to. So it sounds like there's an effort to draw smaller areas that are 1 square mile, which is, I think, a much more reasonable way to do that. And so I think better and more well testing data for the areas not served by public water systems is the first one. The next one is, I think consolidation is really the preferred alternative for, I don't know what percent, many of these systems, if not most of them, and at least the little ones. And we didn't have the ability or the time to figure out what the cost implications of that were and how that compared to the cost estimates that we included. So I think those are the two things that are most important to spend a little more time on.
Hi, Dr. Tom Williams, Citizens Coalition for a Safe Community, LA. My biggest problem is median household income and how it relates to your surveys? Because how many employee housing does the agricultural areas have? And who owns the meter? Who owns the well? You made reference to their house or their well, and ownership doesn't imply 40,000 or less per year household income. So I'm quite concerned about the sampling and actually where the money will go. If it goes to a well in a farm housing facility, it goes to the owner of the farm. It doesn't go to the users of the water. And I'm quite concerned about, you might say, money's going to agribusiness, money is going to owners of houses that are rented to those with less than 40,000 income a year. And how reliable are your violations when you consider that renters, employee housing probably don't complain to the water boards, but it is the owners of the wells, owners of the tap, owners of the meter that might complain. So I'm quite concerned about how you reflect affordability and how the monies will actually be allocated later on to solve the problem of the users of the water who are subject to disease, metals accumulations, and things like that.
Well, I feel like my presentation is a success, at least in one case, because that's exactly the point I was trying to make, is that how you define who you're trying to help is, I think, the most important task. I will say one thing, though, about the household income. So the household income data is from the Census Bureau, and it's based on the people living in that household, not the owners of that household. So in that sense, I think, the census data is not perfect, but it's certainly the best we have, and it's not just based on the owners. There's certainly transient workforces that the Census Bureau may well miss, and I think that is an important consideration. But as I said, I think your main point that we, the state of California, need to be very aware of who we're trying to help, and who we can afford to help is very important. We should focus it on those communities that really need it, and there's some communities that might be in violation that we decide can't afford to help themselves and don't need state help.
Yoram Cohen, UCLA. Indeed, I think that it's a heroic effort, and as you indicated, very complex and a lot of uncertainties. So what I wanted to ask you, within the work that you've done to estimate costs, what are the main areas where you sense that there are significant uncertainties that impact your analysis? And what I mean by that is that typically, if one can bound the various factors that you have, then you can run various type of simulations and get a probability distribution so that you know whether the conclusions that you have make sense or not, and with what level of certainty or uncertainty you're reaching conclusions.
Yeah, I mean, I think that's a good point. As I said before, I think that the two main areas are the domestic well users and how many there are and what contamination they're subject to, and then the consolidation cost. But I think the bigger point that using something like what we developed to identify those areas that make the most difference is a way of prioritizing the effort that the State Water Board is engaged in right now. And so, we can figure out, at least in our model, what if the treatment costs for small water systems are twice or more than twice what we have estimated based on the original data that the Water Board had? How much of a difference does that make? And if we do that, it's not going to double the whole estimate because there's lots of other costs in here. That might tell us to focus, let's focus there. Or maybe if we figure out that our estimate of the number of domestic well users is off by 20%, that's really the most important factor. So we can use sensitivity analysis to help kind of narrow in on the things that are the most important to keep looking at. It's not something that we're currently planning to do. This is a project that actually, frankly, my outstanding colleague, Katrina Connolly, did the work on, but she's being a mom right now, so I get to be here and present it. And it is actually work we did a couple of years ago. But it's important, and I'm certainly happy to try to contribute to this effort in some way if I can. So it looks like we're done with questions, so thank you all very much. And I think these presentations will get sent out, and there's contact information for me, so I'm happy to follow up if there's more questions.
Thank you, Matthew. That was great. So our next presenter is Dr. Laura Feinstein. She's a senior researcher with a water program at the Pacific Institute, an Oakland-based research organization specializing in sustainable water management. At Pacific Institute, Laura's work has focused on drinking water and sanitation for disadvantaged communities, the water energy nexus, the California water policy. She was a Science and Technology Fellow with the California Legislature and a California Delta Science Fellow. She holds a PhD in ecology from UC Davis.
Thanks. Thank you. Hi, everybody. Thanks for coming today. I'm here to talk about a relatively new project on solutions for underperforming water systems that Pacific Institute is undertaking with California Urban Water Agencies. Katie Porter from KUA is here today, funded by the Water Research Foundation. Next slide. So I'm going to give you an overview, first the project background, and then some of our preliminary results and approach that we're taking in our analysis, and then give you a sense of our next steps for the project. Next slide. So a little background on the project. The project partners are Pacific Institute, KUA, and Water Research Foundation. We're all nonprofit organizations dedicated to solving water challenges with high-quality technical information. We have different organizational histories and strategies, but share the belief that everybody should have safe, affordable, accessible tap water, and that communication across interest groups can help achieve that goal. Next slide. So to give you a quick sense of the steps of this project, our site visit to see some of the underperforming systems was in March of 2019. I obviously failed to fill out a couple dates here. The first advisory committee meeting was about a month ago, and we are currently just getting started on data analysis. Next week, we'll have a workshop to convene some of the thought leaders in this issue. We expect preliminary results in late summer, and then a final report in winter of 2020. Next slide. So our research goal is to develop a systematic approach to identifying solutions for small underperforming drinking water systems. Next. And we have 4 components to the analysis. First is the toolbox, which is to talk about the ranges of solutions that are available for underperforming systems and identify those criteria that distinguish a system as a potential candidate for a particular solution. We'll undertake some data analysis, particularly focusing on hotspots for drinking water challenges in the state and potential regions for water partnerships. We plan to focus on a few case studies, 33 persistently underperforming systems, and thinking about how to link them with potential solutions, and then make a series of policy recommendations on how to improve the enabling environment in California for small water system compliance. We are particularly interested in the role of the higher performing water utilities in water partnerships as a strategy towards improving compliance in the state. Next slide. What aren't we trying to do with this project? We're not interested in weighing in on how to fund the unmet financial needs of the small water systems. Regardless of where the funding ends up coming from, we think it's important to begin thinking now about how to start implementing solutions. We're trying to leverage some recent research. As we're hearing today, there's been a lot of useful research going on, and we are trying to engage and review both the research done by other organizations and also build on some of the recent research our organizations have done. Pacific Institute recently took a look at how to measure progress on universal access to water and sanitation in California that took a service ladder approach to ranking water quality in the state. KUA put out an issue brief that focused on how to classify small systems by their persistence of violations. And the Water Research Foundation is currently working on a project on water utility partnerships as a resource, putting out a resource guide and toolbox on those with an eye to seeing how to increase the political will for water systems to voluntarily enter into partnerships when those are useful. So to introduce the problem, I mean, people in this room are quite familiar with this, but of course, small water systems in California struggle with consistently delivering safe water in the state. There's close to 3,000 community water systems in the state. Of those, 2,500 serve under 10,000 people. And many have difficulty complying with the Safe Drinking Water Act. As this map is showing you, all those colored dots are showing you small water systems that have had long-term problems with a given analyte. Next slide. And sort of the major underlying problem for the small water systems is always the question of technical, managerial, and financial capacity. The revenue that a system takes in tends to correlate, of course, with the number of paying accounts that they hold. The amount that a system charges for 12 CCF is not vastly greater when they have 25 connections than when they have several thousand connections. So the amount of revenue a system is taking in from month to month tends to go up as the number of paying accounts goes up. So the smaller systems end up trying to deliver reasonably safe water on a far more limited budget every month. Next slide. So moving on to some preliminary results from our analysis, or really what I'm more going to walk you through is our overall approach and give you a sense of what we're going to be doing in the upcoming months, because the data analysis of this project just started in the past few weeks, really. Next slide. We're going to take a look at a toolbox of approaches. And so you've sort of heard some of the other speakers talk about this today. The first sets of tools in the toolbox are things that are not treatment focused. They're physical consolidation or managerial consolidation, which we're putting under the subcategories of water partnerships. There's also management reform, which can be, for example, appointing an administrator. That might be relevant for a system that has long-term administrative problems, but doesn't actually seem to have necessarily an extremely limited financial capacity, and potentially with new administration could reform its ability to deliver safe water. The next set is a new water supply, so that could be potentially a new well or engaging in some kind of water trading with a nearby water supplier. And then the last three sets are treatment focused, so either optimizing an existing treatment system, capital improvements to a treatment system, and then either point of entry or point of use treatment systems. Next slide. So we're going to talk a little bit more in depth today about water system partnerships, because that's where we've started to do a bit of digging already. And just to define those for everybody, water system partnerships come in many flavors and varieties, so people often use different terms as well for these. There's both the physical consolidation and the administrative consolidation aspect. So the physical consolidation is actually connecting your infrastructure and having one shared water supply between two former water utilities. The administrative consolidation is some kind of blending of administrative capacity, which can be relatively informal, such as an agreement just to cooperate or to buy supplies together to decrease the costs, all the way up to some kind of ownership transfer, which would be the most formal transfer of responsibility. As our previous speaker was saying, much of the way that the analysis is sort of based, it depends on kind of our definitions and where we choose to focus. So I'm going to walk you through what we're choosing to focus on, and you're going to see a lot of commonalities and also some differences in how we've chosen to sort of slice and dice our target group of interests, which I think should lead to maybe some interesting discussion about, for the State Water Board, how do they want to focus their needs assessment. So for our analysis, we've chosen to focus on the small water systems, specifically the community and the non-transient, non-community water systems serving under 10,000 people. Next slide. And we also are, in our spatial analysis, going to look at the location of disadvantaged unincorporated communities, which are settled low-income rural areas that are either not identified as census-designated places in the 2010 census, or they are small communities within a comparatively wealthy census-designated place. So these are areas that, if they are not overlapped by a water system, are most likely reliant on either state smalls or domestic wells. They are low income. Presumably, they're highly unlikely to be able to correct any water quality problems they have themselves, and so we want to consider when they are in proximity to an area that we think has high potential for a water system partnership to make sure that we are taking into consideration those communities that are nearby. Next slide. So we have created 4 performance categories, ranking systems from satisfactory down to, actually it's not unsatisfactory, it's unacceptable is what we have at the bottom. It starts with a UN, so we always end up switching it. We considered short-term acute violations as a greater health risk than short-term chronic violations. We wanted to take into consideration some of that nuance between the acute versus the chronic problems. And we also consider long-term violations a greater health risk than the short-term violations. The approach that we took is vastly simplified compared to this model approach I'm pointing to here, but I do think that as we're moving forward with starting to think about more elaborate strategies for defining where to first focus efforts, we should be thinking about moving beyond just the classic, is a system in compliance or out of compliance, into taking into account some of these more nuanced considerations. And this is something that the United Kingdom has only recently adopted, and I think is an interesting model that brings into account a lot of these considerations. It's the Drinking Water Inspectorate Compliance Risk Index, which is a very interesting approach that I think is a bit more sophisticated than how we've been used to thinking about measuring risk in drinking water. Next slide. So these are our 4 performance categories. At the top is satisfactory, and that would be a system with no out-of-compliance quarters during a 4-year period. Then a moderate level performance would be no out-of-compliance quarters for acute analytes, and no more than 1 out-of-compliance quarter for a single chronic analyte. Marginal would be between 1 and 11 out-of-compliance quarters for any 1 analyte, acute or chronic, and then unsatisfactory, or I think I already said, I'm pretty sure this is supposed to be unacceptable, but I apparently cannot seem to bring myself to type unacceptable, is greater, at least 12 quarters out of compliance for any 1 analyte, acute or chronic. And this is, as I said, out of a 4-year period. Next slide. So there are 3,000, this number seems a little different. This is because this includes the non-transients. So there's 3,988 small systems, both community water systems and the non-transient community water systems. That's why this number is a little higher than that number I was showing you earlier, serving 2.6 million Californians across the state. And it's a little hard to see all of them, but we've color-coded them by their performance category, with, of course, red being unacceptable and green being satisfactory. Next slide. So where do the small systems fall into these performance categories? So as I was saying, the total is about 3,988. 2,500 of those are community water systems. This is ones for which we actually knew a location. And 6% were in the unacceptable category, 25% in the marginal category, 1% were in the moderate category, and 68% were in the satisfactory category. Next slide. Oh yeah, and here's the population served by the small systems by performance category. It's 2.6 million people served by these small systems. 2.3 million are the community water systems. So a chunk of that population is drinking this water in what we call the non-transient system, so maybe at a school, at a place of work or something, but not in their home. But the majority of these are community water systems. And what you're seeing here is about 227,000 Californians are receiving water that is in the unacceptable category from a small water system, or about 10% of those served by the small water systems. The majority, about 68%, receive water in the satisfactory category. Next slide. So we've been doing some spatial analysis. This is a zoom in on one particular water system of interest, the Delray Community Service District. And starting to ask a few questions from a spatial perspective about which areas are candidates for partnerships. So some of the questions we're attempting to address are, for systems with unacceptable quality drinking water, how many water systems are within a reasonable partnership range? And of course, one of the threshold questions there is, what is a reasonable partnership range? So that's going to require examining some of the literature about the distance people often go for partnerships. And it's going to inherently require some assumptions about that distance is a good proxy for whether or not you can enter into a water partnership, which of course there's a lot of complexity there when you actually get on the ground and start looking at these systems. But we're going to take a look at, for example, a smaller threshold of distance as an area that would be have potential for a full physical consolidation. There might be a medium distance that's appropriate for an indoor water only physical consolidation, and then a larger distance would be appropriate for some sort of regionalization partnership. We're also interested in asking whether there are key areas around the state to target for partnership zones. So a key area might be an area that has both a large number of people receiving water that is in the unacceptable category, but also have some water systems in the vicinity that are relatively high performing, that could bring some additional TMF capacity in that area. We're also interested in asking whether these target areas for partnership zones happen to intersect with the disadvantaged unincorporated communities. So as you can see on this map, for example, Delray Community Service District is a small water system. It has long-term problems with delivering safe drinking water. It is both in the vicinity of some higher performing water systems, and it's also in the vicinity of a number of disadvantaged unincorporated communities that are currently reliant on wells for their drinking water. If a partnership zone were to form in this area, it would benefit potentially not just Delray and these other systems that are highlighted in red, but also those disadvantaged unincorporated communities. Next slide. So we also are going to focus in on 33 case studies. So why did we pick those 33 for our case studies? We mainly are focused, again, on the systems in the unacceptable category. And we chose to focus on systems with greater than 200 connections for this study because those serve 80% of the population in that unacceptable category. Next slide. So I won't ask you to read through this enormous thing, but I'm just saying that these are the 33 that we're focused on and that they cross a range of counties and represent a number of different types of contaminants. Next slide. This is just the last bit of the list, and next. So in the unacceptable category, 33 systems serve more than 80% of the population. So we chose to focus on those as the first sort of cut or target for this study. Our questions are, which are candidates for partnerships? Which are candidates for administrative solutions? And then what are the relevant treatment options, and what are the typical costs for a given treatment option? And as I have learned today, we will be looking at those EPA numbers as perhaps an extreme bottom floor estimate for those costs. Next slide. And last, I just want to point out what the next steps are so you know what to expect from this study. Next slide. We will be having a workshop to gather input from stakeholders next week. We will be putting out some draft results in late summer and then a final report in winter of 2020. Next slide, and that's it. Thank you very much. I don't know, is there time for questions?
Yes, absolutely. Maybe a question or two.
Hi, Laura.
Hi.
EPA has worked with Division of Drinking Water for some time on a list of utilities that have been extremely problematic based on some of the same criteria that you're utilizing here. Did you reach out to DDW or to EPA Region 9 with respect to the lists that you're using?
No, I wasn't aware of that list, but now that I know of it, oh, Katie Katie Barley has more information on that.
Hi, Bruce. Yeah, we did reach out to EPA Region 9, have not been able to secure that list, but was given reference back to the Human Right to Water database, which is what our data is based on.
But Bruce, if you're able and willing to point us to the right person to talk to about taking a look at that list, that would be really interesting.
Do one more question?
Hi, Brad Coffey, Metropolitan Water District. I looked at the list real quickly of the 33, and it seemed like a big number of them are 1,2,3 trichloropropane. I wonder if you could comment on that, because I wouldn't have thought that would have been the contaminant for this kind of long-term non-compliant systems.
Because the MCL only came into effect relatively recently. So we had the monitoring data for TCP 123 from before the period when the MCL actually went into effect. So we were using the monitoring data from years prior to the MCL going into effect in order to make the assessment of which systems were in that unacceptable category. There were a couple of contaminants where we sort of had to make some judgment calls, as we've been hearing, about what should be in and what should be out. Mainly TCP 123 and hex chrome were the big questions, because with hex chrome, of course, there was an MCL, and then it's no longer in effect and it's being reconsidered. So that's going to definitely be something we're going to have to be careful about, sort of both putting it in and taking it out and showing the sensitivity to whether you include or exclude. But as a general rule, what I was mainly showing you included both hex chrome and TCP 123, because we're sort of trying to get ahead of those problems. I mean, first of all, TCP 123 is obviously going to be, in this upcoming couple of years, a huge issue for so many of these systems in terms of getting into compliance. And then with the hexavalent chromium, the MCL may end up being enacted at a less rigorous level, but it's presumably going to go back into effect at some point, and we'd sort of rather be looking forward to that problem than ignoring it for the time being.
Great. Maybe any other questions? Okay, well, thank you.
Thank you.
So we're going to break for lunch now. We are going to start at 1 p.m. sharp. For everybody who has one of these, hang on to it so you can get back into the building and up here lickety-split. So see you at 1 o'clock. Maybe thank you again to all of our panelists. Is really great. Thank you. Yes. For our webcast, we will be back at 1 p.m. sharp. Hey, welcome back, everybody. Maybe we can take our seats and we'll get started. We're going to do a few minutes of questions via email before. Yeah.
Hi.
All right, so we're going to get started here this afternoon. And maybe I'll give everybody another minute to just take their seats. Yeah, your seat is up here, Dr. Long.
Somewhere.
So we're going to start this afternoon's session. Well, maybe one more time, thank you to all of the presenters in our morning session, and thank you to our presenters, our upcoming presenters. But we're going to start this afternoon with some questions that came in via email, I think mostly on the subject matter we covered this morning. And so Michelle is going to read those off, and then Eugene is going to either answer or maybe direct it to one of the other presenters if they're still here.
Hello. So this is, we had one question from the internet where it was, when will the PowerPoints that are going on for today's workshop, when will they be available? So within a week, we should be able to get those all up online onto our needs assessment webpage. And then the other question that we have, well, Lucio's not here, so I'll have Darren answer it. So one of the questions from was, is the application grant information publicly available? And I know you're not DFA anymore, but.
Application grant.
Right, so application grant information for DFA.
Yes, it would be, but it'd be in separate files, so you'd have to contact DFA to be able to ask them to pull it and look at it. And the other hard part, I think, that Lucio mentioned is that it's each project, right? It's not, you're not able to screen it easy. You got to go to each one.
Okay, and then we had a question for Eugene, which was best available technology for 123 TCP. And that question was, do you foresee a GAC cartridge being developed? What would be your criteria for that based on other constituents in the water?
So currently for VOC removal, there are certified devices available. So those are under NSF NC 53 standard for drinking water treatment devices. But the standard for those cartridges is generally removal down to the parts per billion range. Given the 123 TCP MCL is in the parts per trillion, we don't know how well those filters will work. And for 123 TCP MCL, it's a California MCL only right now, so there is not a huge demand for the device to be able to remove TCP. So the market is not there to drive someone to develop a certification standard. But there are custom, for the device certifiers, they do have custom challenge tests available that they can do it. So I think if we create a market for it and work with some of the manufacturers, they'll be willing to certify some of the devices so that we'll be able to get some device list. Absence of that, I think right now the best option is to select devices that's certified for VOCs and then plumb them in a lead lag configuration so you can monitor at the midpoint and with a flow meter to figure out how much capacity it will work at a particular water systems. Once you have that, then for that specific site, you can operate to a conservative quantity. So maybe you prove it that it can work up to like 1,400 gallons, then you can operate down to 1,000 gallons and change it out every time with a single cartridge so that it will be easier to install at all the subsequent sites.
Thank you. Lucio, I'm going to have you come down for this other question. It said that you pointed out that DFA can assist with rate studies and TMF training, but those efforts may be insufficient to address the deficiencies of resources and experiences in operating and maintaining more complicated treatment systems. I would like to ask all the presenters to address the question, but I think, Lucio, since you're DFA, I want to send it to you. When evaluating the needs of a system that is applying for capital funding, is any assessment made of the ongoing operation and maintenance of the capital improvements and the cost of necessary resources and expertise to meet the O&M needs beyond 15 years? Do you want me to read that part again? Yeah. Okay. When evaluating the needs of a system that is applying for capital funding, is any assessment made of the ongoing O&M of the capital improvements and the costs of necessary resources and expertise to meet the O&Ms beyond 15 years? So I think, or yeah, you want to take it?
Yeah, I'm going to let my supervisor, Nicole Morgan.
Go, Nicole.
So, good afternoon, Nicole Morgan with the Office of Sustainable Water Solutions. And so when we're looking at funding a project, we are looking for the life cycle of the project. And so if it's 15 years or if it's 20 years, we're looking at that specific life cycle. We're not necessarily looking past that, but we're also not necessarily disregarding that portion of the project. And so part of the question, I believe it was, are we looking at the ongoing O&M past the 15-year mark? Only, so that part of that is if the life cycle of the project is looked at, is felt to be, if it's a 15-year project, we're only looking at to the 15-year mark for the O&M costs. If it's, a 20-year project, we're looking at that 20-year mark. We're not looking past that point in time.
Thank you, Nicole. Okay.
Great. I want to remind everybody that you can keep submitting your questions via email or via the comment cards in the back. Also, something I forgot to mention this morning is there is a sign-in sheet in the back. If you haven't already done so, maybe during the break or on your way out, you could jot your name down there so we can keep track of who was in attendance and who participated. Thanks. So we're going to move on to our afternoon presentations. And again, we'll stick with a similar format of maybe a question or two after each presentation, depending on time. And then we will certainly have a long period of questions after our final presentation so that we can have plenty of discussion, everybody's voice can be heard, and all the questions can be raised. So our first presenter this afternoon is Tara Henry. She is a senior scientist with Corona Environmental Consulting. She holds a master's degree in soil science and has over 15 years of experience solving drinking water contaminant and regulatory compliance challenges for utilities. She holds several leadership positions in the American Waterworks Association, where she is chair of the Inorganic Contaminant Committee and a member of the Technical Advisory Committee to the Water Utility Council.
All right, thank you all for coming back after lunch on a Friday afternoon. I really appreciate you being here, and most of you are awake for now, so we'll try to keep it that way throughout my presentation. I'm actually going to talk about two projects today. The first one, I only have a few slides. It's a consolidation project that we're working on for Water Foundation. We just started this project, so we're very early on in this project, but it's a very quick turnaround as well, so we will have results very soon here, and we'll be working with the others in the room that are working on similar projects as well. And this is supposed to work now, so yay. Yay for small victories. Okay, so for the consolidation project, the primary audience is the legislature. This will feed into the current bevy of bills that are out there to assess how much money is needed for a lot of ongoing solving small water system challenges projects. The objective is to really quickly look at the feasibility and order of magnitude costs for physically consolidating out of compliance systems within compliance systems. So we're still working through the assumptions on that, and we'll probably be adjusting those assumptions after we do the first round of data analysis. So the approach is to categorize systems of in compliance and out of compliance, and then look at the system size, the population, number of connections, the issues they have, and we'll also try to look at some of the economic data as well. So if they're DAC, SDAC, to the extent that we can, that data is not always as readily accessible as might be desired. We're going to be using a GIS approach, so we'll be looking at the boundaries that we have already publicly available, and then we will put in a roadway layer and make the pipeline go along the roadway. We don't want to do any overland main. That just isn't going to work. And see how far away these systems really are from a system that could potentially take them. And of course, we're going to have to make some assumptions about what it means to potentially be able to take a system, right? Like what percentage of customer connection increases is acceptable, right? If it's, you're doubling the system size, that's very unlikely to be to be workable for most systems. And then we'll be assigning costs based upon size and distance categories. So, we'll be looking at kind of the less than 1 mile group and then the 1 to 3 mile group over 3 miles. In this particular analysis, we're going to assume that's, beyond the cost feasibility for now. So this is just an example. The blue system would be the receiving system. The yellow system there is one of the systems listed as out of compliance on human right to water. So you can see the yellow line actually goes from one system to the other. That's where the pipeline would go. And you can see that for this particular example, we didn't just run it from the edge of the boundary to the other edge of the boundary, because for most systems that's not realistic. They wouldn't have a main big enough right at the edge. So those are kind of the types of assumptions we're setting up, and we'll do some sensitivity analysis to see what more like the range would be, because it's not, we're going to not come up with one magic number, because we don't have enough data at this point to do that. And the second project I'm going to talk about, spend most of the time on, is our Proposition 50 funded nitrate treatment project. We are partnered with UC Davis for that project, and Jeannie Darby's here as well, our university partner. And I have more complete acknowledgements at the end because we have several of our participants here. So I will go ahead and get into that one. So nitrate is a persistent non-compliance issue, particularly in California, and the ongoing operations and maintenance is very expensive. It's not like you can just install treatment and we're done now. It's really expensive. So we're looking at other options as far as managerial consolidation for these small systems to partner with bigger systems and get their costs down by getting this sort of economy of scale that they can't get on their own. And the idea here is to really try it out. So just nationwide, nitrate MCL violations are shown on this map. So this is actually data from 2013 to 2016. And the red dots are for systems that have been out of compliance for 3 years or more. And you can see a lot of those dots are in the Central Valley of California. And then there's another group over by Salinas. So not too surprising, but a big challenge here for us in California. And as far as looking at across the states, this is, again, the same time range. California does have the most systems out of compliance, or did during that time frame. I'll go ahead and put my money on that we still do have the most out of compliance nitrate systems. So for nitrate treatment, really my first option, if you come to me and say I have a nitrate problem, I will tell you avoid treatment if we can. Can we drill a new well? Can we blend? Can you tie to someone else? Like, you don't want to treat for this constituent. But if you have to treat because you're not close to someone else and we can't drill a new well where you are because all the water's contaminated, then we have to get into treatment. So initially this project was really conceived of for systems that need treatment. None of these systems have other options. It's just about $5 million in grant funds to install and operate. Originally, the project was for all strong base anion exchange systems, and this project's really unique in that we have the O&M costs within the project for 3 years. And the idea there is we'll really be able to test this out. So the project will pay for the O&M costs, so we'll get real cost data for these small systems under this consolidated management approach versus a non-consolidated management approach. So how will we minimize the O&M costs? They'll be sharing an operator. They'll be sharing brine disposal, so that this brine disposal truck will make this kind of, we call it a milk run. It's kind of a little less friendly than a milk run, a brine waste run. And then they'll be sharing salt delivery costs. So that really saves a lot on the contracting costs. The small utilities just aren't going to get a good deal because they're so small. So these are the 3 systems that will be receiving the grant funding. There are a few bigger systems that already have this treatment installed. So that's how we're getting this economy of scale, is really by partnering with those bigger systems. And we're helping them with reporting, and the contracting will help them as well. So that's why they've elected to partner with us. So this is how we thought the project was going to go when we originally conceived it. We thought, great, they're all going to be the exact same system, strong base anion exchange in 3 locations. One's a school and 2 are systems. Ionics was going to be the equipment provider, and we also had the system of RRR that may want to participate. So the ones marked in brown you're going to see in the next slide go away. So Ionix actually declared bankruptcy and R dropped out of the project. So those are the initial changes. Now I'm going to show you the next slide. These are all of the add-ons that have happened since this project started. So now that Ionix is gone, we need to do procurement and bid documents and go to all the equipment providers that might be willing to work on this project. We have to do full site design, which originally was under Ionix's piece of the project. We have changing costs. And in Tonyville, originally we knew they had nitrate and perchlorate. Turns out they also have arsenic pretty much just above the MCL. Woodville, we knew they had trichloropropane. We didn't know that they didn't have a real tank, so they really need a tank also. Rio Bravo Greeley School District, they came up with trichloropropane after the project started because that was their first sample. They were already in violation on sample number 1, as it is sometimes for small systems. They had very high concentrations. They were already on bottled water, so don't worry about the kids. And then we were really looking at this. For Rio Bravo, could we do a partial flow treatment? Could we separate out the irrigation system and not treat all that water that's going to their soccer fields and only treat the water that's going to the buildings and the houses and the swimming pool on site to save costs? We also looked at strong base anion exchange for all the sites in more detail, and we determined that for Rio Bravo, there could be a corrosion concern. So we started looking at reverse osmosis, and then we would have a calcium carbonate contactor on the backside. So that's where we've landed for the moment on that one. Okay, so I'm just going to walk you through Tonyville a tiny bit. We won't have time to go in depth on all of these. What you're looking at is the existing surface water treatment plant, and where I was standing in this picture, the 2 wells were behind me. So the 2 wells are on the same site. You can notice there's actually railroad tracks there. And so if any of you have done pipeline work under a railroad track, it's not good, not pleasant. Luckily, they already have a connection from the wells over there. So that's really great news for us, so we can put the treatment unit over there at the existing surface water plant. So this is their current system. They get water out of the Bryant-Kern Canal. They have a surface water treatment plant that's quite old, like 80s, 90s range. It's still working fine. It's in compliance. Unfortunately, the Bryant-Kern Canal has to go down for maintenance once every 3 years or so, so they have no surface water during that time, and they have to use those contaminated wells. So their customers haven't been able to drink the water during that period. They do have that reservoir on site, which is terrific. So, this is run by a bigger irrigation district, so the staff's much more well put together, which is great. But that's not normally the case at these small utilities. So this is what we're proposing here. There are 2 kind of configuration options. We need to take out the perchlorate, which can also be done with strong base anion exchange, but it will be a throwaway resin, so we'll have that as a separate piece of the treatment. And then we'll remove the nitrate and arsenic through the unit there. So we're showing regenerable here. That's generally what you need to do for nitrate because you have to regenerate so often. So there's a brine tank up at the top there, and that's used for regeneration when any of the beds are exhausted. And then you generate this waste brine down here, which is shown in the yellow. So there's a lot more to it. We're regenerating sometimes every 24 hours, several times a week on some sites. So that's a lot of pieces that are moving and could break, a lot of valves, a lot of programming. So it's a challenging treatment unit to operate even in a big system. Okay, so for Tonyville, the unique challenges, the existing surface water treatment is relatively high quality, but it dries up periodically. The cost to treat their surface water is actually a lot less than what we're going to be able to do here for strong base anion exchange. So that's a challenge that we need to address. What happens in 3 years when our O&M funding goes away? Do they just tell DDW, well, too bad, we have surface water that's in compliance, and then this unit sits there? How is that going to work? Or are they going to raise rates to make this work long term? And the perchlorate and the arsenic potentially in the brine can limit the disposal and commingling possibilities, so that's another challenge we need to overcome. So hopefully the perchlorate will be removed in that first piece, but we'll have to make sure the arsenic's going to be all right. Based on calculations, it should be okay. So reminders and lessons learned. For this type of technology, smaller doesn't make it simpler, okay? So we still have to have all the same controls and safeties and online analyzers, and the operator will still need to be certified to the same level. So, and the needs are actually unique at each site, right? So we can plan these things in our offices all day, but until we get out to the site, it's hard to know what unique challenges each system will have. And we want to make sure that all of the details are considered, so like the Rio Bravo Greeley School District addressing the corrosion control issues as well. And we want to make sure we're balancing the treatment plant sophistication with operational requirements. So these actually could be operated by small systems in the future. And hopefully having an operator that's servicing all these units will help because he'll get more familiar with the units as well. So there's also still a really big need in the marketplace for innovation in nitrate treatment. A lot of them do not really make anything for these lower flows. They aren't going to make a lot of money, you know, it's just, since it's not economically feasible for the small water systems, the market space hasn't developed yet. So we're trying to address that in our bid documents and trying to bring some not IPO protected, not intellectual property protected methods to this so that we can really make it more repeatable. Okay, so I'm not going to get too much into the affordability other than I want to show you some costs. So I want to make sure you understand some of these affordability metrics. There was a whole other workshop about that, and we could really spend a lot of time on that. So I'm not going to, though. Oh, there it goes. So affordability is a subjective concept. So there's all sorts of different metrics. I'm going to present the ones that have been used in the past that are the most straightforward to do right now. We've done the calculations on lots of others, and I have that in another presentation. So if you're interested in that, I'd be happy to share that with you. And there's not really, you know, one sharp line. We have to make a line, but in reality, it's a continuum, right? So just to say, this is where it's affordable, this is where it's not. There's some gray area. And it's a problem for large as well as small systems, but definitely in these small systems. So it's a growing concern because water bills are already rising faster than the consumer price index, and wages aren't rising that fast either. So water's getting less affordable. And the real income of the poor, it is going down. So that's another challenge as well. So this is a little bit about the systems. Rio Bravo is a school. So highlighted in yellow there, you'll see the median household income is actually quite high there. But that doesn't really matter because they're a school, so they can't charge the parents for water treatment, right? So effectively, they're still economically disadvantaged because there's no way to get the money from the parents to the school to pay for this, so it has to come from elsewhere. Tonyville has a median household income of about $48,000, and we also did the 20th percentile household income, which in some slides is called the lowest quintile income. And the reason for that is the income isn't always this nice normal distribution. We can see kind of this bimodal distribution, which I'll show you. So that's why it's important to look at what's going on in these lower income households as well. And Woodville, you can see the median household income is only about $28,000, and the 20th percentile income is actually $15,000. So pretty economically disadvantaged, severely economically disadvantaged community. So here's the income distribution. California as a whole is shown in green, the solid. And then the communities are shown, Tonyville's in the blue, Woodville's in the medium colored turquoise, and then Rio Bravo Greeley School District is in the lighter colored turquoise. So you can see Rio Bravo tracks with the state quite well. The other two definitely are shifted to the lower income end of the spectrum. Oh, okay, there it goes. So this one's just showing you our anticipated treatment costs. Tonyville is shown in the first area there. The dark blue is the current bill, and you think to yourself, maybe $12.19 seems really low. They have this funny way of billing where one connection's for two houses. So the two houses together would have a bill of $24, and they somehow split that amongst themselves. It's a very small system, let's say. So Woodville, their current bill is about $26. So already probably your gut's telling you their bill isn't paying for the improvements that need to happen in the infrastructure they already have. Yeah, that's probably right. We know it's right, we've done the math. So number one, their existing bill's already too low for what they have. So it's way too low for improvements. For Tonyville, we anticipate that the average water bill could go up to about $80, $81. And the error bars there are actually the range of 5 different quotes we got from different vendors. So that's the median there. And unfortunately, now that Ionics is out of the picture, our lowest number there is gone. So when we go back and get the real bids, we won't get that low end anymore. And Woodville, you know, that bill's a little more reasonable. It's a little bit bigger system, so $43. A lot of you probably pay more than that right now. So, but to them, it's a big increase, and they definitely had heartburn when they saw these numbers. Okay, so where are these costs going? This is all O&M cost, right? Because the capital's paid for by the grant. This is just the O&M cost that's increasing the bills. So we're going to look at with consolidated management and without consolidated management for Tonyville, just as an example. So with consolidated management, we expect that the annual operations and maintenance expense for this system will be about $69,000. Without the consolidated management, it would be around $136,000. So that's a big difference. We've made a dramatic improvement, we think. We haven't gotten to enact this yet. These are the vendor quotes we've gotten so far. We think that consolidated management's really worthwhile. But you can see labor's a really big component here, right? So if there's a way to maybe, you know, have division of drinking water, help with operators and send operators out, that could help reduce the cost. So there's some creative ways that maybe we can improve this number further in the future. And of course, there's kind of this salt and brine disposal piece that we have to have. You can't get rid of that. We can try to minimize it through a variety of ways, but we have to do that to treat the water. Okay, so affordability metrics, we've looked at way more than these, but these are the ones that are existing. So the ones you'll be seeing on the graphs are the 1.5% of median household income, which is what the State Water Board uses, and 2.5%, which is what EPA has used in the past. These are just some others for reference. All right, so affordability without the grant. I just want to show you that the grant is doing something. It's important. What we're providing on the capital subsidy side is important. But another way to look at this number is that when they have to replace this equipment in 20 years, they're going to have some funds to do that, or they have to go and get another grant. So if they didn't have another grant in the future, this is the kind of thing they're looking at. So what you're seeing on the y-axis there is the household water cost per household income in percent. So that's their percent of income they'd have to spend on a water bill. Okay. So this is without the grant, but I just want you to think about it for a moment here. If you're living in Tonyville and we aren't able to do consolidated management and there wasn't a grant, it would be 10% of the median household income would be spent on water. So just take a moment to think about your income. If you had to spend 10% of your income on water, like how grumpy would you be? I'd be super grumpy. So it's way too much. So you can see how much we are there above the 1.5%. All right, so this is with consolidated management, so it does make a difference, and this is without consolidated management. So there is an improvement there, but it's definitely still not affordable. And this is affordability with the grant, so that is a huge help. This gets us part of the way there. The first one is with consolidated management, and the second one is without consolidated management. And what you're looking at in the dark blue is the median household income, and the stripes, that's the 20th percentile income. So we just put that there so you get a feel for what's happening to the lower income folks and not just the median household income. So you can see we're much closer to that 1.5%. We're not all the way there though. We're making some progress. It's a tangible difference with the consolidated management and the grant. So that's with consolidated management and without consolidated management, we anticipate. Okay, and then this is for affordability with the grant, just looking at the type of subsidy that would be needed to bring it to that affordability level at 1.5% of the median household income. In Tonyville, with consolidated management, we would need about a 24% subsidy. So it's noticeable. So this is with consolidated management, without consolidated management. So in summary, the grant that's needed to pay for this capital is crucial. We can't do projects like this without that. The nitrate market space really needs to develop further in order to provide things that are going to be appropriate for these smaller systems. The consolidated management approach is expected to lower O&M costs, but even with the capital grant and the consolidated management, the ongoing operations and maintenance for these systems is considered to be unaffordable. So I think this is really important in the current context of the legislative bills that are being considered and the other options that are being considered on a statewide basis to address this type of problem, because there really is no money available right now for this ongoing O&M. So, And so let me do my acknowledgements list here. There are lots of other people that could be on this list. I've narrowed it down a little bit. So Dr. Jeannie Darby from UC Davis is here. And from Corona, Craig's probably watching. Vivian's going to watch later, and Chad's here. Rio Bravo Greeley School District is one of the systems, and Lindsay Strathmore Irrigation District, the Woodville Public Utilities District, because they're obviously putting forth a lot of effort to get this project done. From Division of Drinking Water, Eugene Luong, Tricia Wathen, Adam Forbes, and Steve Gambroni and Mally Vu, who are here. We'd really like to thank them because they're on our calls all the time, participating and working hard on the project as well. And this is actually a picture from Rio Bravo Greeley School District. That's their oil-lubed well, which needs to be replaced, and their existing tank. I'll take questions now.
Great, let's take a question or two.
So the question was, do you want me to repeat it? Could you hear? So for the consolidated management, he wants to know sort of who the administrator would be. For the first 3 years, we'll be administering that. So we'll set up the contracts and get everything rolling. I think after that, there's kind of a lot of things we need to sort out on that. They will be sharing an operator, so they're going to have these contracts with the brine disposal folks and the salt delivery folks and the operator. But then how would other utilities join, right? Like how do they get their little card to join the consolidated management club? So I think we'll see how it goes, and there are folks that are interested in doing that type of work long term as well, but we haven't established exactly how that will go. First, we'll see if it works, and we'll sort that out.
One more question? I think somebody may.
I was just wondering, are you just looking at public water system consolidation or also individual wells consolidation as well?
For the consolidation project? Well, it depends on the data we get. So at the moment, we have access to the public water system data. So that's where we're going to start. We'll see how long we can keep going and what additional data we're able to add in. We are hoping to do at least a case study where we take one of the bigger systems with a pipeline to a smaller system and look at the wells along the way. So I think hopefully we'll be able to at least do a couple of case studies. So at least we have some anecdotal feel for how many smaller systems and private wells might be able to be picked up. But the data set for private wells is challenging.
Great, thank you. So if you have more questions for Tara, remember we'll have a lengthy question session at the end of the day. So our next presenter is Kevin Berryhill. Kevin is a principal engineer at Provost and Pritchard Consulting Group, specializing in water quality and treatment. He holds a master's degree in mechanical engineering and is licensed to practice both mechanical and civil engineering. He has 20 years of experience, including groundwater, surface water, small and large systems. Those projects have included dozens of feasibility studies evaluating costs for consolidation, new sources, point of use, centralized treatment, and to mitigate a wide variety of water quality challenges. So, Kevin.
Well, good afternoon. I appreciate the opportunity to speak, and hopefully this will add something meaningful to the discussion we're having here today. So let's see. Okay, so everybody else has taken a crack at who are the troubled water systems. And without getting political or philosophical here, from my standpoint, doing engineering work for these water systems, these are the groups that I see that are going to be the biggest challenge. The first one's the no-brainer. I don't think there's anybody in this room that doesn't recognize there are small disadvantaged communities with serious water quality issues and an affordability problem. So I think we're all in agreement there. But some of the other systems that I see and I run into frequently where there's issues, they may not fall into that category. There's large disadvantaged communities. For those of you that aren't aware, once you exceed a population of 10,000, a lot of the funding opportunities go away. Grant funding typically goes away at that point. And there's some of these systems that are disadvantaged. For example, Los Banos is one I'm working with. They have 13 wells. They were a great system for a long time with no issues. Nobody lost any sleep over the Sea of Los Banos. Well, when the hexavalent chromium, or I should say the regulation formerly known as hexavalent chromium, came out, 13 of their wells went overnight from being in complete compliance with the system until to being completely out of compliance, 2 to 3 times the MCL. So again, that's their entire water supply. They only have 13 wells, they're all out of compliance. So that system is seriously challenged by the changing regulation, but maybe doesn't get looked at in the same light as the small disadvantaged communities. The other one I'm becoming more aware of are the small mutuals. These are collections of homes, typically in highly rural, way out in the middle of nowhere, 10 to 40 homes that have joined together and they have their own water supply system. And many of these are not disadvantaged. They may have extensive turf, some of them might have horses, but they're very TMF challenged, very tenuous management of these systems. I don't want to disregard or disparage the efforts that their management puts into it, but this is much closer to volunteering to be a crossing guard or organizing a community bus run. These are the folks that have signed up to manage these mutual water companies. And so that works if all you're doing is paying for a well that doesn't have drinking water challenges. The second you get a compliance order, suddenly the administrative burden just goes through the roof on that volunteer. And if anything, we're starting to see issues where these volunteers are just not interested. Take it away. I don't want to be responsible for this water system anymore. And so those are going to be a real challenge. And TCP has hit those systems really hard down in the Kern County area as an example. So what is my perspective? So my perspective as an engineer, I think it was mentioned earlier, one of the first steps in a lot of these projects is a feasibility study. So it's one of the very first steps. We come in and we look at all the available options to deal with an issue. It's usually a compliance order, but it could be some other water system emergency like a well going dry. And the things we look at are non-treatment, we look at blending, we look at consolidation, drilling new wells, point of use, point of entry, and as a last resort, we start looking at centralized treatment. And we collaborate with the system, we collaborate with the State Water Resources Control Board Division of Drinking Water. And so what I'm presenting on today really are some generalizations I'm bringing out of dozens of these. Just in the last few years, we've probably done dozens of these feasibility studies. So I'm trying to pull out some important points from those, but I would caution against any overly generalizing, because every one of these systems is very unique, and it is a little dangerous to generalize too much. So here's kind of the different options that are available in order of increasing cost. At the bottom of the pyramid, we have source replacement and consolidation. These are kind of our best options. Now, the difference between whether we want to push for consolidation or source replacement, obviously there needs to be an ability to replace the source. But if there's not good technical, managerial, and financial support for the system, consolidation moves way up to the top of the list. If the system, for example, like Los Banos, has a very strong managerial structure, they've always been well organized, typically replacing their source is going to be looked at a little more closely than consolidation. Next, we look at point of use and point of entry. That's going to be less expensive in a lot of cases than centralized treatment, particularly when we're talking about the smallest systems, particularly when we're talking about arsenic and nitrate and difficult to treat contaminants. And finally, last resort, centralized treatment, and this is where it gets really expensive and really uncertain. So the rest of this presentation, I'm going to kind of start from the bottom up. I'm going to describe each of those and just some general observations again for each of those different alternatives. So we'll start with source replacement. It used to be you could just go out and drill a well, and maybe a hydrogeologist would look at some historical data and say, yeah, I think you should drill a well this deep and you probably won't have any contaminants. But the aquifers are starting to look more and more like minefields. Every time a new regulation comes out, it limits even further which formations in the aquifer are viable for a water treatment supply. And so these days, on almost every case, we recommend what we call zone testing. It may be called different things by different firms. But in essence, you're drilling a very deep hole. In some cases, we go down 2,000 feet. And you start testing from the bottom up, sampling the water at each formation to try to find water that meets drinking water standards. And this is a good example of where we might be able to stretch our buck a little further. So one of the deficiencies I see in the existing funding system today is you can only get planning funding for a test hole. You can't construct a finished water supply well with planning funding. That has to be construction funding. Problem is, if you're going to do zone testing, you need to do that early in the project during the planning phase. So what happens right now is we get a well driller out, they do the zone testing, then we throw away all that work and we waste the test hole, and we go back and during construction we start from scratch with a new well driller, a new hole, a new mobilization. A simple change like, for example, allowing under certain circumstances construction of a finished supply well during the planning phase would result in a substantial savings. Suddenly, instead of adding 60% to the cost of the well, maybe you're only adding 15 or 20% to do the zone sampling, which is money very well spent. Some of the limitations of zone testing, this kind of approach, there is no guarantee good water exists. You can go down 2,000 feet and you could find nothing but problems all the way up. But there's only one way to find out, and that's to try it. And it's certainly better than centralized treatment. You've got to use a qualified well driller. In our experience, there's only been a few we've worked with that have been able to do this successfully, where we get results that are reliable. We actually trust the results we're getting out of this. And then you do need a fair amount of field observation, where you might not need that if you're just drilling down to a known depth. So those are the limitations. Give you an example. This is just one example of how this works. So this is in the Tulare Lake Basin, which has some of the nastiest water in the state. This was a case where we drilled down to 2,000 feet or more than 2,000 feet. We were trying to avoid disinfection byproducts, water that came out of the ground looking like tea. The color was 120, which 15 is the regulatory limit, so almost 10 times the limit on color. And they had arsenic over the limit. So when you drill down deeper and you do the zone testing, you could see in this case, the color starts to drop off. So that's good. We know as we go deeper, the color goes away. It starts to get a little more complicated when we look at arsenic. And this is where it really shines. You can see here, you wouldn't figure this out unless you did something like zone testing, but you go down and you figure out there's this narrow window around 1,800 to about 1,900 feet where you can get below the arsenic MCL. Now, everything comes with a price, and this is where we start to run into problems. As regulations get tighter and more constituents start getting more closely regulated, it's getting harder to not sacrifice something that's important to get away from something else that's important. So in this case, as we went deeper, we start to see saltier water. This community has to sacrifice some salt in their water to get away from their arsenic problem, which from a health-based standpoint, this is a good trade-off. Also, just interestingly, when you drill down that deep, the water gets warm. In this case, we actually got 90-degree water out of the ground. That's what the community is drinking. But as I'll comment on later, when you drink water that looks terrible and smells terrible, suddenly having a water that's a little warm and a little salty, that seemed like a really good trade-off for that community, and they have not received any complaints about the salt or the temperature. Consolidation. Again, for managerially challenged systems, this is really something that needs to be looked closely at. The fewer systems that the state has to regulate, I know that they'll be happier. And for these systems, I think a lot of them would really like to get out of the drinking water business. There are challenges, though. Cost is not always the challenge I think that it's made out to be. So typically, 1 mile of pipe is less than $500,000. And I'm talking pipe for fire flow. This is like 8-inch pipe. This is good-sized stuff. You look at treatment, putting in a treatment plant, and you could easily spend several $1 million, and then the community is hung with the operating costs for the rest of time. And so the cost aspect of consolidation isn't usually, in my experience, the limiting factor unless the system is really out in the middle and nowhere. There's other obstacles. There's the regional extent of the water quality issues. So it's easy to say, let's consolidate with the next system over, but there's a good chance they have the same compliance order and they're struggling to deal with that compliance order. Systems rarely cooperate, and I'll go over some more reasons for that in a minute. And then there's technical issues that have to be worked through. Hopefully this is legible, but let's go through some of the issues that come up with consolidation. So from an operational standpoint, you've got the water quality issue. So if you've got a water quality challenge facing a small system, then the larger system next door, again, probably the same water quality challenge. You got to have adequate capacity. In a lot of cases, you need to construct a new source, whether you're consolidating or not, because the receiving system does not have adequate supply to serve you. You've got to deal with fire flow. This is an interesting one. A larger community, if they're providing fire protection water and fire hydrants for their customers, it's an interesting liability and publicity question Can you serve a smaller system but only run a smaller pipe to where even though they're the same water system, they don't have fire protection water? In a lot of cases, I think you do need to provide the fire protection water. The system infrastructure, typically these small systems, they don't have meters. There may be issues with the service connections. All that has to be done from scratch before a larger system is able to accept them and even figure out how to build them. Metering, fire hydrants we talked about. Customer perceptions. Almost every case that I can think of, both the receiving and the small system have had concerns about the rates going up. And so on both sides of the equation, folks are worried that this is going to affect their water rates. Bill payment, small systems are notoriously difficult to have everybody paying their bills. In a lot of cases, it's like pulling teeth to get some of the customers to pay their bills. Larger systems don't want to accept that responsibility. They don't want the headache. And then opening the floodgates. This is kind of a classic one. If you let that small system in and you consolidate with them, what basis do you have for refusing the next small system in the area that comes along and asks you to consolidate? So these larger systems are looking at this. If I do this, what precedent am I setting, and how many other folks are going to be asking to consolidate, and how big a headache is that going to be? And then you have legal restrictions. Are they outside of their service area? There's LAFCO issues. There's all these good things that have to be worked through. Next, I'll just briefly talk about point of use, point of entry. And we've been involved in a number of these projects. It turns out a lot of systems, particularly commercial and industrial, they're already doing this. So we'll go out after they get a compliance order, and they've already got the point of use devices set up because that's what people want to drink. The most common point of use technology, and I think Eugene may have alluded to this earlier, it's the classic under sink device that's shown on the right here. It's kind of the best of all worlds. These are reverse osmosis and activated carbon. And between those two technologies, there's very few contaminants you can't take out of the water. So the reverse osmosis pulls out your metals, your nitrate within limits, uranium, salts. At full scale, it's not really viable because of waste, but when you're only treating 6 gallons a day, I think I have this on a later slide, you can assume maybe at least 5 gallons of waste for every gallon treated through a reverse osmosis plant like this. But 6 gallons a day treated is still only 30 gallons of waste. So it's at least in the realm of manageable and feasible. The activated carbon will take out your volatile and your synthetic organic contaminants, pesticides, takes out taste and odors. The water tastes great when it comes out of these devices. And you combine those together and you basically have an under sink point of use device. So very versatile, very inexpensive. Here's just a chart that shows what they'll take out. I mean, as far as I can tell, 1,4-dioxane is one of the few contaminants, and we really don't see that commonly as an issue. Arsenic, a lot of them will advertise they won't take out what's called trivalent. This is arsenic that hasn't been oxidized. My experience in pilot testing is they do. Even the ones that on the package say it won't work, works. So very few things we can't take out with it. How do you select a device? So first thing we do is we look at the California Water Treatment Device Registry. And for point of use, there's a lot of devices on the list. There's a lot to choose from. So if anything, it's a challenge for these systems to figure out how they're going to reduce that down to a manageable list. My advice is down at the bottom of this sheet. We actually found that when we tested devices that we just went and bought from Lowe's, from Home Depot, they performed every bit as well as the ones that came from the proprietary water treatment suppliers that you find knocking on people's doors and leaving flyers. And the beauty of those devices are when they need replacements or they need replacement cartridges, it's a simple trip to the hardware store versus you're trapped with a supplier that has a proprietary system. Things that you need to have, built-in flow and TDS monitoring. This has been a big issue in the past. The devices work well, but very few of them come with built-in monitors, which the regulations require you have. And the monitors that are available aftermarket are junk. We would put in the devices, they'd work great, but picture the undersink of your kitchen. Every chemical and nasty detergent that you have in your house is crammed in the undersink area of your kitchen. And so that environment's pretty harsh on electronics, and these TDS monitors and these flow meters, usually the battery compartments are corroded within a year. A lot of them have stopped working. So that's a shortcoming of the technology, and maybe one that the state could do more to help identify or even sponsor the development of devices that do what we need it to do, and they're reliable. Capital costs very low, $200, maybe another $100 to install these. I think the EPA cost estimating tool probably overestimates what it costs to do a point of use project. Replacement cartridges, you're looking at maybe $6, or I'm sorry, not six, $60, maybe to $100 every 6 months or a year. The RO cartridges tend to last very long, in my experience, longer than the 6 months advertised. So there are limitations. So they're not allowed for residential applications where there's volatile contaminations, because the concern is you're going to breathe these contaminants when you're in the shower, and you don't put these point of use devices on the shower, you put them under a sink. One interesting little nuance to this has been trichloropropane. In theory, in the regulations, it's called a synthetic organic contaminant, which tends to mean that it's not volatile and this isn't an issue. But the state has consistently identified that as being a concern, and so point of use is not allowed in a residential setting for trichloropropane, and that's proving to be a challenge. Some other limitations, the NSF certification, you have to take this with a grain of salt. If you look at the fine print on the NSF certification, they perform it using basically perfect water that doesn't exist in nature, almost distilled, go and grab that distilled water off the shelf in the grocery store. It's something not far from that they use for testing these, and then they spike it with the contaminant. So they may not work on all water qualities, and it does need to be pilot tested in each system. They also use chloroform as a surrogate for all VOCs. So you'll look at this list of dozens of VOCs that are tested. They really only test one. They test chloroform, and if it removes that, they assume it's good for everything else. So far, that hasn't been a bad assumption. Trichloropropane is one that still kind of remains to be seen. Again, because of the low levels we're targeting, is it really valid to use chloroform as a surrogate for that contaminant? Nitrate removal effectiveness is limited. If you have really high nitrate levels in the water, the RO built into these is not adequate to take it out. And depending on the pressure of the water supply, it may affect how efficiently it removes some of these contaminants. Point of entry. This is a different beast. So now we're talking about treating all the water going into a house or a building. It's relatively common in commercial and industrial applications. It works really well there, as a matter of fact. Small RO systems, activated carbon canisters. It's a little difficult to implement in residential settings, and I have not seen a lot of these that have been used in a residential setting. Issues, the device availability is definitely more limited to point of use. Now we're getting into the territory where we're going to have a hard time finding a viable device. Reverse osmosis is out of the picture now. You're just generating too much waste for it to really be practical, unless you're an industrial user that has another way of disposing of maybe a larger waste stream. Building plumbing corrosion is an issue. I don't see this talked about a lot, but if you were to treat the water going in an entire building through RO, that water becomes a lot more aggressive, a lot more corrosive than it was before, and you have to worry about premise plumbing. And then solid waste disposal might become an issue. Some of these have arsenic adsorptive media, for example. If you look at point of use, the assumption is it's a residential household waste. You throw it in the trash can. If you look at point of entry, where you've got a larger cartridge, in my mind, it's uncertain whether that becomes a hazardous waste that needs to be handled more officially through proper channels. And out of all the technologies, I'd say activated carbon is the one that has the most potential when it comes to point of entry, particularly for residential. So take this chart with a grain of salt. I just wanted to highlight a few things. This is from a project I worked on some time ago for nitrate treatment. Actually, it was nitrate, arsenic, and uranium. So classic example where you don't want to treat it in a centralized plant. 34 homes. Capital cost was going to be like $750,000, but that's after we've taken all their non-potable use and plumbed it separately. So there was a bunch of infrastructure that would have to go in before that treatment plant was ever constructed. Point of use, I would estimate it was about $15,000 is what they spent on it, between buying devices, installing devices. They had to put a chlorinator on one of their wells. But it starts to get much more economical when we're talking about point of use treatment. Annual O&M, you're comparing $35,000, which is maybe a little on the low end of what it would have cost for a centralized plant, to $10,000, which is probably on the high end for POU. And you can see where the flow rates come into play here. So centralized treatment, we might be talking about treating 75 gallons a minute. Point of entry, it gets down to 5 to 7 gallons per minute. And when you get to point of use, you're only talking about 6.5, 7 gallons a day. So it's a lot easier to accomplish that when you're talking about the smaller volumes. And And then, as I mentioned earlier, for waste volume, in the point of use application, you're talking maybe 30 gallons a day for each of these devices. It's not negligible, but it's manageable. Centralized treatment, you've got 5,000 gallons of brine, or point of entry, maybe 1,000 gallons per home, which, we're talking about RO here because we need to remove nitrate. Working with the enemy. So part of the problem I've had with the point of use, point of entry approach is we're having to work with companies that use questionable marketing tactics to sell their products. I mean, you've probably got a flyer on your home at some point that says your water's unsafe to drink. Even if you live in a major metropolitan city with a perfect record, somebody's trying to sell you water, and it's usually got a picture of your little kid drinking out of a fountain on the front to make you feel guilty and buy the treatment device. These are the same people that we're trying to buy equipment from at this point. They have very little technical knowledge about the product, and they tend to use misleading marketing tactics. And so you have to kind of filter that for the community. These are just some examples. I didn't want to show pictures. The pictures are great, but I was afraid I'd get sued by one of the manufacturers if they saw their product on here. So working with the customers. Compliance, 100% compliance is 100% compliance. And I've done this exercise when I've talked about this before. Think about your neighborhood, your greater neighborhood. Everybody has one person in the neighborhood that there's nobody that could pay you enough money to go into their home and deal with them on a regular basis. This water system has to deal with every single person. And so there's a lot of liability issues and other issues associated with that. You go into some of these disadvantaged communities, they're economically disadvantaged. There may be some crime issues that could happen with the larger, even wealthy communities. You walk into a house that's got a meth lab in it, but that water system operator has to go into that house at least once a year to maintain the device. Is there room under the sink? If the device leaks, who pays for that? Because the water system owns and operates that device. It's like an extension of the drinking water system, the point of use device. So if it leaks and ruins the floor or creates toxic mold, that's on the water system. That's not on the homeowner. And so these are some of my big concerns when it comes to point of use applications, particularly in a residential setting. And I know it's being done, but in my mind, it's only a matter of time before some of these legal liability issues maybe rear their head. Let's see here. So in summary, for point of use, point of entry, kind of my view is it's great for commercial. This is a really easy solution for a lot of commercial facilities that are having problems. Contaminated private wells, it may be the only option that they have. It works great. We know it takes the stuff out of the water. Once you get into a residential setting where maybe all the homes are under common ownership, like one of the examples I worked on was a dairy with employee housing. Best case scenario, there's only one person that owns all the homes, but even then there were challenges due to the different homeowners. It was difficult to schedule and get in to service the devices. There were some homeowners that resisted. So those are kind of questionable. And then I just have serious concerns with the broad application of this to a regular residential community where there's individual homeowners, potentially 100 of them that are affected by this. So just briefly, I'll talk about centralized treatment. Cost and operability vary widely. I get questions a lot about how much does it cost to treat arsenic in a water system. There is such a huge range. You've seen some of the error bars on some of the other presentations. They're bigger than the original cost in some cases. Some classic examples, nitrate's always going to be expensive. There's just no good options for centralized nitrate treatment. It's a painful process. Arsenic and hexchrome. I'll give you one example for hexavalent chromiums. Tested 2 systems. One of them needed to regenerate their ion exchange every 8,000 gallons. The next system needed to regenerate it every 60,000 gallons. So there can be an order of magnitude difference in the efficiency of these processes depending on which system you're looking at. And then there's disposal challenges like uranium, where you're generating a radioactive waste that has to be disposed of. In reality, there's really only one supplier in California that does that work because they have the appropriate licensing. And then there's really regionally challenging water. Tulare Lake Basin, it's a real mess what's coming out of the ground over there in most places. And there's multiple contaminants. I mean, one system, had aluminum, disinfection byproducts, arsenic, iron. I'm sure I'm missing a couple. That's just in one water supply. So these multiple contaminants greatly increase the treatment challenge. And then waste disposal could be a major complicating factor. So some closing observations. One, before I forget, I didn't put it on the list. A lot of times when we're trying to get costs down, we're looking at innovative, cutting-edge technologies. And those technologies end up being proprietary. And we've seen it twice now. I've seen it twice just in the last year, where one of these suppliers, was mentioned in the last presentation, Ionics, they went bankrupt. They've installed some systems. It's a relatively specialized system. They're not around to support it now. The same thing has happened in the past. So we need to recognize when we're going with these really cutting-edge, innovative technologies that there is a risk that it's not going to, the suppliers of those systems are not going to be around to support them down the road. And we've got to question whether it's still a good choice to put that in, given that situation. The Division of Drinking Water collaborative model carried over from the California Department of Public Health works great. I work with a lot of different regulatory agencies, and I've got to say this, Division of Drinking Water is more of a carrot than a stick approach, and it allows us to meet with them ahead of time and have honest dialogue about the options without worrying about negative consequences. I could walk in and tell them that there's a water system that should be permitted, but they're not. And they're not going to go and try to penalize or fine that system if they're trying to bring themselves into compliance. I encourage the State Water Resource Control Board to continue that kind of a culture, because it really does make these projects more efficient and more cost effective. And I'm just hoping that that carries forward. Public acceptance of projects greatly influenced by aesthetics of the water quality. So if the water looks and smells terrible, generally people are much more willing to support different alternatives or even pay more money. If it's just an invisible contaminant that's a little over the MCL, we get my grandmother drank it for years, she was fine. And so there's a certain difference between, and it's ironic because some of the their aesthetics are not health-based, whereas the arsenic and the chromium are health-based. But sometimes the consumer perceptions are flipped on that. The current State Water Resource Control Board financial assistance program fails to address the larger disadvantaged communities, in my opinion. Yes, there's economies of scale. The Los Banoses of the world are more able than a smaller system. But when you take out 13 wells at once, I refer to those as scorched earth regulations. There's some systems that are going to be completely affected. We're not talking just one or two wells that are knocked out. We're talking the whole system knocked down at one time. And I think there needs to be some kind of assistance more than there is now for those kind of systems. And then the last one's a little out of date, I'll be honest, because it used to be that waste disposal was a big concern of mine, that it drove the costs on a lot of these projects. We were lining ponds that maybe didn't need to be lined from a practical standpoint. I'm happy to say that last year there was, at least the Central Valley Regional Board promulgated a low threat discharge rule that for the first time had some waivers for water treatment backwash water. I think that's a real step in the right direction, and I hope there's a lot more coordination between those agencies to help get the cost down, at least from the waste disposal standpoint. So with that, I'll take any questions.
Let's have a question or two if anybody has one. Sure.
Yeah, for something like arsenic, for centralized treatment on things like arsenic, do you feel there's value in doing like column studies or pilot studies, or just going straight to design? And how do you decide when to do one or the other?
For arsenic, almost always you need to. Arsenic's one of those contaminants where there are things that will interfere with treatment. If you're looking at absorptive treatment, there's other things in the water that can interfere with it. There was a case mentioned earlier about an absorptive treatment system that was constructed, and then they realized the operation costs were going to be way higher than what they thought. They had to replace the system. In my opinion, arsenic is just too risky to go forward without testing.
Another question out there?
Oh.
Yeah, Kevin, great context on point of use. I'm curious how you view California water systems now considering point of use as a long-term solution, with the change in California allowing it as a permanent solution rather than an interim solution now. It's a unique first start here, whereas other states have had systems in place for more than 10 years. Do you see that changing in the systems that you're watching that have implemented it interim, now thinking it carries forever?
I think in most cases they do think it's going to carry forever. I mean, they recognize that every 3 years it needs to be reevaluated. But as a practical matter, unless a miracle nitrate solution presents itself, some magic media comes out of nowhere, it really is long-term. And I think if it's a good choice to begin with, on day one, if it's a good choice to put point of use, point of entry in, it'll be a good choice 10 years from now, 20 years from now. If it's a bad choice, we're going to be living with it, and it's going to be a struggle no matter how long they're implemented.
Maybe one more question back here.
I was just wondering, have you considered consolidating on a smaller scale, like 5 houses, but still consider a private well? So like if you were to have installed one well, but it's connected to multiple homes, I was just wondering if you looked into that.
So are you referring to consolidation of private wells, private homeowners?
Right. So if you're looking at individual wells, instead of consolidating on a large scale, maybe on a smaller scale where there's 5 or 10 homes connected together in one well. Because I've seen that done before, but it's mostly among private well owners who come together as a community and decided that they're going to build a new well when they're all share the operation maintenance costs and the water treatment costs, and there's one person who's knowledgeable about maintaining the system.
Yeah, so what you're describing is basically the mutual water companies I mentioned at the beginning. Those mutuals are not faring well under regulatory compliance orders. So if there's a groundwater contamination issue, it's probably going to be a challenge to take a bunch of private well owners, bring them together, and form any kind of a water system that has an ability to manage itself. They need somebody. They need to be a much larger entity before they can provide the technical managerial, and financial support they need. I've not looked at it, though. I've never been involved in a project where we looked at consolidating private well owners together. Sometimes they get picked up as part of consolidation projects. So if you're running a pipeline 3 miles to connect a small water system to a large water system, one of the questions that has to be answered is, what about all those little ranch homes along the way? Do every one of them get to connect to the system? That does come up, and that does have to be handled.
Because the largest problem that I see for consolidating private well owners is that some of them are outside the city limits or just way too far away to consolidate.
That's definitely the case.
I think Division of Drinking Water has seen a few instances like you're talking about where there's a community and everybody's on private wells, and there are some success stories about the contamination in those private wells, and then putting in municipal level infrastructure for what is 30 or 50 homes or something like that, and seen some success there. So there is economies of scale and strength in numbers in that way as well. So thanks again, Kevin. A lot of that was my day-to-day, so I really appreciated that. So our next presenter is Dr. Cohen. He's a distinguished professor of chemical and biomolecular engineering at UCLA, where he is also on faculty of the Institute of the Environment and Sustainability. His current research program focuses on smart distributed water systems, high-performance membranes, self-adaptive water treatment systems, water reuse, and upgrading of impaired source water to provide safe drinking water to remote and disadvantaged communities.
Well, thank you for the introduction. And I should say, starting this morning, when I listened to Darren and Eugene and all the speakers that came afterwards, everything that I was going to say has already been said. So I'm canceling my presentation. But what I'm going to do is go fairly quickly through probably some of the same issues that have been talked about, but I'll point out some differences based on our experience, and primarily which emanates from doing work over the years in various locations around the San Joaquin Valley and Salinas, and working now with disadvantaged communities of the size that the last question pertained to. Those are very small communities, 5 homes, maybe 8, 10 homes, all rely on a particular well. So the comments that I'm going to put forward, and I guess I have to say next. Oh, it works, all right. Yes, it does. So I'm not going to go through all that has been said, but if we talk about permanent solutions, everyone has said that we need to worry about affordable water costs to residents. Of course, we have to have a robust water supply. And one of the issues is, of course, with regard to monitoring. We've heard a lot about point of use, and that you can change the cartridge once every so many months. And I don't know how many of us would be willing to basically rely on such a promise that the system will work and that you will have sufficient drinking water that is safe without knowing at every point in time, in fact, that it is safe. So it brings about the issue of monitoring. We've heard about centralized monitoring, centralized treatment, and the question, of course, there also is monitoring, how effective that is. And in all those projects that we're talking about in terms of permanent solutions, we have to think about the time to planning, permitting. And this is one of the things that I've learned, over the years working in those projects, that one of the key issues was not technology. One of the major hurdles, and for a good cause, because we need to ensure that we have safe drinking water, is the length of time that it takes to go through various negotiations, the permitting, working with the communities. And specifically, you have small communities that have smaller water systems and, of course, short on technical and managerial abilities. So you heard about capital costs. I'm not going to go through that. Operation and maintenance with regard to operators, which is, of course, very important. There's also issues with regard to emergency response, but also the admin cost. In terms of a community itself, especially when we deal with small communities, can they govern, themselves? Can they have any kind of structure that will allow them to do that? The notion that if you have a water operator, you'll rely on the water operator, I think is a bit of a dream, because in many of those cases, you have to have an oversight over the water operator, themselves, in some of those cases. So there's also the issue of information dissemination with some of those communities that, as we heard, disadvantaged communities. In some cases, there is a language barrier, and you have to deal with that as well. So we heard about searching for a new well, for a new community well, and the issue that there's no a priori assurance that the new well will be of the desired quality. So that's an issue. Whether or not drilling a new well is costly, that depends on various factors, such as how deep do you have to go. But there are also issues about rights. In other words, the well on site, in many of the small communities, the area is fairly small. So the notion that they can drill another well is not very realistic. So if they have to go off-site, can they have an easement, right, for example? They will have to negotiate with somebody who is nearby. And I'm not talking about consolidation. I'm just talking about having a well off-site. And in fact, one of the small communities that we work with have the well off-site. They have an easement right. So what is the cost that is involved in that case? And there is also the conveyance for piping from that off-site well. The other issue is water pricing that may be imposed by the well owner, which is not under the control of the small community. So that's an uncertainty that is brought into place. We heard about physical consolidation or annexation, however, we want to consider this issue. And I've learned here today that there is quite variability in terms of the cost of piping. In our interviews of various officials around the Salinas area, we heard numbers from $0.5 million per mile to $1 million per mile. But the question is, how much additional costs are maybe involved in the infrastructure that we have to deal with? Also, the question is whether or not you have a willing neighbor who is willing to work with that community and to provide them with that water. And the previous speaker has spent quite a bit of time talking about this important issue. So agreements, negotiations may be complex and lengthy, and they also add to the cost. And of course, there is uncertainty with respect to the operational and maintenance cost and the prospects of potentially increased costs after consolidation. In other words, the remote community, the small remote community, disadvantaged community may not have control over water pricing. We heard a lot about point of use, and the main point that I would like to bring into that is that point of use devices don't give you the guarantee that they operate properly. Checking them once every 6 months is wonderful, but when you work with such systems, you don't have that guarantee. So the question is, what risk are you willing to accept? That 1 out of 1,000 systems may fail? That 1 out of 10,000? So it's an issue of risk that one has to address. Monitors that exist are primarily for salinity, and we heard from the previous speaker that they're not very reliable, especially when you're talking about under the sink. Another thing that you have to remember is that when you have such devices under the sink, for example, in the case of reverse osmosis that was mentioned, they operate only at about 10% recovery, or 15%, maybe 20% for the best systems. So in fact, what you're doing is you're only treating a small amount of water that you're going to use primarily for potable uses, for drinking. So you have to ask yourself, and I'm serious about this, you have to ask yourself, if you knew that your water well or your water source was contaminated, would you be willing to just drink water that has been treated and then use water for every other purpose knowing that it's contaminated? Well, again, that's a decision that you have to make, and you have to ask yourself, is there a risk in it or not? So that is an important issue to consider when one is suggesting such an approach. And of course, the cost that is involved in such a distributed solution of who's going to maintain it, who is going to be the responsible party, is the homeowner is going to take care of it, is going to be an outside water system operator or a company that is going to do the routine checks and so on. So I'm getting to the point of entry, and again, those are not my most current slides here, but it should have said wellhead / point of entry for water treatment option, because in many ways that there are similarities. So the main issue here, and this is how I'll move forward towards what I'm really interested in conveying to you in terms of our efforts in the area. The issue when we get to small communities, whether we use point of entry, whether we use wellhead treatment, is that in small communities, the number of customers is small. So in terms of absorbing the cost, that provides you with a challenge. In terms of the small communities taking care of their own water systems, that's a challenge too, because the expertise is not there. So we have been working over the last several years on the concept of virtual consolidation. And I don't mean admin consolidation or consolidation via administration. I mean taking water treatment to the next level from a technology viewpoint. And what that means is that the systems that are at the wellhead are actually operated remotely. They are monitored remotely. So the expert is available to all systems at the same level of expertise. So the systems that we monitor are all monitored from a central location. In our particular case in this work at UCLA, later point in time, it may be a system operator, but they are remotely monitored. The systems basically are self-adaptive, so that if anything goes wrong, all the notifications, everything of that type is automated. There is even fault detection and isolation, which basically means that we try and figure out if things are about to go wrong way in advance to actually do asset management as is common, to do that all in an automated way. And the reason for that is to reduce the costs, and I'll get into that in a minute. So the question is, imagine this, and I'm saying that ahead of showing you the particular slide, that you have multiple small communities, But I'm sitting here with this screen in here, and if I had a keyboard in here, I can control, I can see all of them, I can operate all of them in real time. All messages in terms of whether or not there are water issues are automatically sent to all the participating stakeholders, including the state, including the regulators, so all information is available. Now, that may sound like a pipe dream, but in fact, this is happening right now in this room. All of you have cell phones, but somebody out there is watching you, watching what you're doing. My cell phone tells me when it's time to go home. You know, it tells me how long it's going to take to get there. It tells me what I need to do in the next hour, that I've been sitting for too long, that I should go for a walk, and so on. So technology-wise, you know, we're really, it's not that far out, okay? It's here and now. So the question is, in terms of physical consolidation, is it really feasible for disadvantaged communities? So the communities that are really candidates for that are those that really cannot go through physical consolidation, or it's infeasible at the present time or in the near or foreseeable future. So they need a solution meanwhile, other than getting bottled water. And sometimes when we talk about physical consolidation, it may take 3, 4, 5 years. And is there an interim solution? Then, of course, both the state board, regional board, county have to be proactive in supporting it, because regulations can be quite complex, and they may need to be flexibility in terms of permitting and in terms of waivers in some cases. And of course, the disadvantaged communities have to be willing communities. The other issue that we've heard before, we heard about various solutions, and I'm going to focus primarily on communities that have nitrate in their well water or in their source water that are the one of concern in our work. So ion exchange is really not a solution for those communities. We considered reverse osmosis, as was mentioned, but in the case of reverse osmosis, of course, you have to deal with the issue of having a concentrate or a brine stream. So you need to minimize that, which means that you have to use technology that will allow you to operate at very high recovery. So in some of our communities, and I'll show you that in a minute, that may be using, let's say, 1,000 gallons per day for several homes. If you operate at 90% recovery, to provide them with 1,000 gallons per day, you have to treat about 1,100 gallons. So that means you'll have roughly about 100 gallons of residual stream. So the question is, what do you do with it? If it's with regard to nitrate, the question is, can you use their septic system or septic tank, you know, to deal with it? So I'll mention that again in a few minutes. So the other issue is whether or not the disadvantaged communities can contribute to any type of on-site improvements or upgrade that is needed for treatment, or if they can get state grants for that purpose, for that capital expenditure. And of course, in the long run, would it be possible to have a satellite water treatment operator that will take care of all those systems? Because if not, then that would not be a solution that would be long-term. So basically what we're looking at, what you're seeing on the screen here, imagine that you have an RO system, a membrane-based system, and the previous speaker talked about RO is only giving 65 to 75% basically removal, but in fact the membranes that are used today in such systems can give up to about 96% rejection of nitrate. So they can meet the goal very well. So you have treatment at the well, and you have a residual. So imagine that residual, about 10% of the total water, into the septic tank. And the question is, will that be a problem? I don't have time to go through all the detailed scientific issues here, but basically nitrate, when it enters a septic system which is under anoxic conditions, will undergo denitrification, because the oxygen is there is what is used essentially for the bacteria that is thriving or needs that oxygen under anoxing anoxic conditions. In other words, they're oxygen deprived. Once ammonia and nitrogen in the septic tanks gets into the leach field, then of course there you have aeration, so you have nitrification, and so you form nitrate. And that's what causes a problem if it then infiltrates into groundwater. So our goal is to make sure that there is no negative impact on release to the environment from the nitrate that enters into the tank. So as I mentioned to you before, multiple communities, so you see communities A through D in this example, all being controlled remotely. So they are consolidated virtually in this arrangement. This is a busy slide, so I'm not going to go through it in any details, but imagine those systems. They're all with sensors, actuators that can allow one to operate and monitor the systems from afar. And if one needs to dispatch an operator, that's done automatically. We've had experience with such system for years. We have a system up at Penoche that is running right now, has been running for 4 years. We basically go and visit it maybe once every 4 months just to clean the spider webs, okay, from inside the system. That's in a containerized system, much bigger than what those communities would need. So let me get into the communities very quickly. They're labeled here as A, B, and C. As you can see, 2 are within relative proximity, and the other is pretty far up. They are the pilot communities with which we are working. They have nitrate above the MCL in one of the sites, just slightly above the MCL, and you see sites A and B where the nitrate is fairly high. Their salinity is also, in 2 of the sites, is fairly high, so you need to basically remove or reduce salinity as well in those sites. So, I'm trying to get it to the next. All right, here we go. So in terms of small communities, in terms of population, somewhere between 16 and 36, homes 8 to 11. You see the distance from the nearest sewage treatment plant, somewhere between 2.2 and 4.4 kilometers in this particular case. So disposing of any residual into a sewer plant is not an option. All those communities have their own local source water. They have septic systems, and they have septic tanks somewhere between 4,500 to 5,000 gallons. So the membranes that are used here are RO membranes. They are high nitrate rejection RO membranes that we have used. And of course, the first thing you do is you've got to go to the field and see if it works. So the first thing that we did before, in fact, installing such system is actually put a system that we've developed, and this is a unique UCLA technology. It allows us to go to 90–95% recovery, but using pumps that are of relatively low pressure, because we use the concept of pressure intensifier with recycling of the concentrate. So we put such a system. This is a fairly small one. You see it in the back of the SUV. It basically generates about 600 gallons per day of drinking water. And what you see in here is actually one of our team members, one of my PhD students who is having his PhD defense next week, in fact, working with the community members in there who comes to see the system and operator. We had a water drinking party there. So they can actually see the system in operation. They see the monitoring, the nitrate levels in real time. And that is critical in order to have the community build and develop confidence in what is being done. What you see at the bottom is a photo of a smart water meter. In all those communities, we have smart water meters so that we know in real time how much water they are using. And I think this is probably one of the few studies in the nation where there is now data for almost 3 years going on water use in such small disadvantaged communities. So we know their peak water usage, we know what happens during the week, and in fact in this particular case with this communities, I was there explaining to them that we saw unusual water usage at one time. On the average, they were using somewhere around maybe 2,500 to 3,000 gallons per day, and on an occasion of a few days, they were up to almost 10,000. And so we inquired, and they were sort of chuckling, and one of the persons who was helping with translation said something. I didn't quite get it, and everybody started chuckling, and I said, what happened? He says, I told them that from now on they can only take 1 shower a week. Well, the story is that they were using, water for washing their cars, and they were using excessive water for other tasks, and part of the project in here was then to also help them figure out how to reduce their water consumption as well. And so that becomes important, but you can't talk about reducing water consumption unless you know the water use patterns. So in this particular plot, what you see is, in fact, 4 sites. I only talked about 3. One of the sites was a particular site in which we also did studies where they also had chromium-6, another issue. So what you see in there, it's kind of hard to see it, and I can't point to it, but you see the nitrate level indicated there. You see the salinity, and then the horizontal dashed line is the MCL for nitrate, and on the right side for salinity. And you see that in all cases, basically with treatment, we go well below the MCL for nitrate, and also well below the 500 milligrams per liter, which is essentially the guideline for drinking water. But of course, when you treat water of this type, you have to remineralize this water, and this is done in those systems as well, both for pH stabilization and of course for a degree of remineralization in those systems. So this is just an example of an aerial view of one of the communities in here. And what you see at the top is just sort of the exploding view of where the treatment system is. If you're thinking about how much space it takes, it's somewhere around maybe 20 feet by about 15 feet or so for the system itself. And then including tanks that are used in there. So let me just, in the last couple of slides, talk about what are some of the key cost issues that are involved in this. Obtaining permits, that's a significant time that it takes to get the permits, authorization, and of course there is a cost involved. Permits for the treatment system, design and operation, establishing compliance mandated monitoring program, which in the case of point of use, it's a different story because they say, well, change the cartridge every 6 months. But the minute that you are at the wellhead, the requirement is that you make sure that there is safe drinking water at all times, okay, in there. So it's not a question of just every 6 months. So we actually have online monitors for nitrates in there in order to prove that issue of safe delivery of drinking water. Then there may be site infrastructure and upgrade to accommodate the treatment systems, the treatment system itself, and of course, a period of commissioning that's also is involved in the costs. And finally, of course, the operation of the water treatment system. So an important part of our project, which is underway, is that of cost tracking. The technical part is pretty well done, but the cost tracking means tracking costs that was involved in planning and design and permitting, in the capital costs for both the treatment system, the upgrade, and operational costs that includes remote monitoring. The whole idea is to show that there is economies of scale, which I'll point to in the next slide. So remote monitoring and supervision, local operator if as needed. And that's primarily for emergency situations or for maintenance when that is needed. And the cost of regulatory compliance, what that may be. And because this whole approach is new, I can't tell you ahead of time right now
what will be the regulatory compliance at the end. In other words, if and when that becomes a routine permanent solution. Communications is very important with the community. So having a community liaison to regularly inform the community and the community outreach that is involved is also part of a cost in such a project. And the maintenance, I've already mentioned, a critical component. So the idea for economies of scale is that the more that you have, okay, the more communities that you have that are part of this network, the lower that the operational cost is going to be, because you're monitoring and you're supervising and you're essentially operating those systems remotely. So reduce capital costs also is important, and the idea is to standardize the systems. Such systems at the wellhead, nowadays, it's very tough just to go and buy a system that'll be just, for that particular application. But there are ways to standardize it, and all the system that we're building right now basically have precisely the same design. They differ slightly in capacity. So we have a virtual network of geographically separated water treatment systems, but they're autonomous. I've mentioned over and over again that there is a centralized but remote monitoring and supervisory control of the systems. So we have basically intelligent control of the systems, and all systems have the same level of expert supervision and operation. And there is the economies of scale. So, in closure, where are we today? The technology for treatment of impaired groundwater for nitrate and salinity reduction has been shown with new small footprint systems that have high recovery. Those systems are currently under constructions. There's been approval for the management of the small treatment residual stream, and there's ongoing monitoring to, in fact, prove the scientific claim of denitrification of the nitrate in the septic system. And a major goal of this whole project is to demonstrate that the annual O&M cost per household in those disadvantaged communities will be below 1.5% of the median household income. We're pretty close. I'm not going to give you a number now because as I showed you, there's such a long list of all the different things that we have to look at and minimize the cost. And as an academic, I don't want to give you a number that I will then regret, okay? But if you're interested, I can just tell you roughly that depending on the system and on the capacity, we expect that the cost is going to be somewhere between $20 to $60, per household per month. Now, the actual numbers, we will know very soon. So thank you.
Great, thank you, Dr. Cohen. Maybe a question or two, and then we're going to take a short break. A question out there?
On the 90% efficiency on the RO, and I think I saw 1,500 milligram per liter influent. So the discharge to the septic, then what's the concentration of the TDS in that effluent? Then it's like tens of thousands?
Factor of 10.
So you're discharging 10,000 milligrams per liter into the...
Yes, but remember, and this is important, remember that all the water that you're pumping from the well, I'd say for the most part, ends up in the same place. So you're splitting the stream and then you're putting it back together. So you're not really having an adverse impact on the septic system. You end up with the same amount of salt in that system, whether you treat it or not. The same is true with nitrate. Whether you treat it or not, you'll put the same amount of nitrate, actually about 10% more, because you're, in terms of treatment, you have to treat about 10% more because you're operating in 90% recovery. So say if the community is using 1,000 gallons per day, and they may end up putting the maximum of 1,000 gallons into the septic system. With treatment, they would put 1,100.
But you point out the nitrate would denitrify theoretically in the septic system, so the nitrate wouldn't return.
The nitrate would be converted essentially to nitrogen. Yeah.
Do one more question?
Whether we personally would feel comfortable with the idea of using water that did not meet regulatory requirements for everything other than drinking in our homes. But I was wondering if there's been any studies actually of risk and exposure by use of domestic water that doesn't meet regulatory standards with a point of use treatment system just for the drinking water.
That's a good question. And so I can tell you that for certain chemicals, yes, mostly for the volatile organics and mostly for the chlorinated. So there have been studies on exposure to chlorinated hydrocarbons at the home and the routes of exposure. You know, in sort of my other life, I also work on risk assessment in environmental systems. So you have exposure in the shower, okay, because of inhalation. We also drink some water when we shower. You have dermal absorption, you know, as well, so that can happen. So there are various ways. You're cooking, and so you can't really know for sure, you know, if somebody who's cooking, is it always a case where they're cooking the water and boiling it, for example, or they're using water directly in their salad directly from the sink and not necessarily the water that was treated through whatever treatment system they had under the sink. In other words, there is no guarantee that the water that is being used is always the safe water that they are supposed to use. That is my point.
Thanks. So we're going to take a short break. We're going to truncate our break a little bit. We're going to come back at 2:50, so at 10 to 3 sharp, we'll start again. We have two more great presenters and then a question and answer period. In about 7 minutes. Oh, it's making me feel wasn't good. I really enjoyed your presentation. I think that for me flowed really well. Tap it, it'll go green.
Fantastic. Appreciate it. Thank
Sure. And then I think you can forwards all of them. Maybe let's take a minute and find our seats again for our last two presenters. I think so. You got it. What's that? Oh, yours will get booted up here in a second, yeah. Let's find our seats, everybody. All right, thanks for coming back from the break so quickly. Our next presenter is Dan Lafferty. Dan has over 30 years of public service experience working for Los Angeles County Public Works. He has served in a variety of positions during his career, nearly all within Public Works Water Resource Core Service Area, where he currently serves as the Deputy Director. Dan is responsible for managing the Los Angeles County Flood Control District, stormwater quality compliance efforts within the county unincorporated areas, and the Los Angeles County Waterworks districts. Dan has a Bachelor of Science degree in Civil Engineering from Marquette University and a Juris Doctor degree from Loyola Law School. He's a registered professional engineer in the state of California and a member of the California Bar. So look forward to hearing from Dan.
Good afternoon. There we go. Good afternoon. So we've heard a lot about some of the challenges that are presented in these small disadvantaged communities. I'm going to give you sort of a case study of what is going on in some of these. And hopefully our situation, while I'm sure is not unique, hopefully it is limited in terms of what some of these entities are actually have going on behind closed doors. So this is the map of the service area for the Sativa LA County Water District. Although it is named the Sativa LA County Water District, it was not one of the county water districts, thankfully. But you can see it's a relatively small community. The 2 wells, and there are no tanks, no interconnections with any other system. That's important as we move forward in understanding some of the limitations that we faced once we got in there. It is a disadvantaged community. Median household income is on the order of about $25,000. So similarly, the ability to be able to afford the types of things that a normal water system would have going on is somewhat challenging in itself. So from the outside, what did we know? There were years of intermittent brown water that was being served to the community. In April of 2018, the Sativa decided for some reason that they were going to flush the system for the first time in years. And when they did so, they completely exacerbated the brown water issue to the point where they had to put everybody on bottled water for a while. As you can imagine, in a disadvantaged community, in a water system that was struggling to get by financially, that had its own repercussions. The extent of the problem was so large that it generated a lot of attention from the media. As a result, there was the state measure AB 1577 that dissolved the Sativa Board of Directors, named the County of Los Angeles the interim administrator. The county then appointed our director, Mark Pastrella, as the administrator. The person who's actually running Sativa today is a gentleman by the name of Russ Bryden. I can tell you that if you look at this, and you can maybe see Russ there in the back, he's the really tall guy standing under the sign. There is no hiding when it comes to Russ. He's 6'9". So when he walks around the community, everybody knows exactly who he is. So once we got in, the first thing that we did is what we call the rapid financial and operational assessment. That was really coming to terms with what did we take hold of here. And it was not good news. It was essentially financially insolvent. It took probably 2 to 3 months for us to even get onto the bank accounts. Even though we had the state legislation, even though we had the action by our Board of Supervisors, the banks were extremely cautious and not especially helpful in getting us onto those accounts. When we finally did, what we found when we got in is that there were no financial records. For the last year, they did not track anything. The way that we had to rebuild those records was, I guess, an exercise in forensic accounting. We took the statements from each of the months of each of the accounts and then called each of the folks that we had written check, that had received a check, and asked, what was this for? As you can imagine, that was a small army of accountants and auditors combing through what few records we had. Their customer accounts were on index cards. And so it was difficult to track all of what was happening with the customers. They did have QuickBooks in terms of their billing. And I will say that to the credit of the customers of Sativa, they are by and large a very, the community pays their bills regularly. And that made things a little bit easier. So, we didn't have to do a lot of chasing on delinquent accounts, thankfully. So when we got in there, basically there's no money in the accounts. They were $60,000 in the red in terms of outstanding bills that had not been paid. And 30 days after taking over, they had a balloon payment on a private loan of $30,000. And their monthly income is about $114,000. As an indication how bad things were, the second day that we were there, the telephones were turned off for non-payment. And so there was a scramble, and I get the sense that it was crisis management down there every single day. Infrastructure wasn't in any better condition. In addition to never flushing, they never exercised valves. The way that they approached a leak was to dig down, cut the pipe, and cap each end. So they did not repair the pipe. As a result, as you can imagine, we had significant issues with circulation as a result when we got in there. The 2 wells that they had on site that serve, those are the source wells, they produce just enough water to keep up with demand. And that also proved challenging in the sense that we could never actually turn off a well to do any sort of extensive investigation of what's happening with the system. We could turn it off for just a few hours at a time before we had people starting to call saying, hey, I've got no water. As an indication of how bad the flow in the system is, the fire flow average is 500 CFS in that system, and there were places where it's as low as 325 CFS. I already spoke about the fact that there were no financial controls. In addition, there were no employee files. There were no contracts in terms of the consultants that had sent bills and that had been paid. They were basically on a cash basis. Okay. So in steps the county. Our Board of Supervisors actually issued a $1.4 million loan to Sativa in December. That was intended to get us through this fiscal year. It's not going to. We're going to have to go back and see if we can have our board agree to add additional financing to help us get through even the end of this fiscal year. So we talked about rebuilding the financial records and the difficulty we had with diagnosing the brown water. At this point in time, we think the main cause is 2 things. One, clearly they've got some sedimentation issues, but they've also got very high manganese. And the chlorination system it's a gas, chlorine gas system. And when we talk about some of these disadvantaged communities and the water systems that are there, the technical expertise was significantly lacking in terms of managing the system. Thankfully, in our case, the county public works, we also have our waterworks districts and our waterworks districts personnel. So we had ready access to people with expertise who could come in and lend a hand as needed. So that actually, you couple that with the financial resources that Public Works had, and it helped us to actually run the system in a way that we felt we were making a positive difference to the community down there. As you can imagine, there was a lot of distrust by the community for the way the water company had been run. The very first community meeting that we had after taking over, Russ walked through what we had found to date, and I can tell you he got interrupted about 4 times with standing ovations from the community. They had had more than enough of the prior folks that had been in charge. So where are we headed? LAFCO dissolved the district in February of this year. And as a result of that, it became a county asset. So it moved from being an independent special district to being an asset of the County of Los Angeles, an asset that we really have no interest in keeping. So we are in the process of putting together an RFP to find an entity who can come in and take this off our hands. We suspect that it's going to be a private water company at that point, which means that we're going to have the PUC review that. Meanwhile, while all this is going on, we're going to still be the successor agency until we can find somebody else to take it over. Our expectation at this point is that it's going to be probably about 6 to 8 months to finish up the RFP. Hopefully we can get it out sometime in the early fall. 4 months for the bid and identifying a successful bidder. And then it's probably going to be a 12 to 24 month process to get it through the PUC. And while there's about $114,000 in revenue, the expenses at Sativa are about a little more than double that on a month-to-month basis. So we are very motivated to get out because all it is bleeding. Okay, so some of the lessons learned here. We knew things were bad. We had no idea how bad. I would say for us, every time we opened up a new file drawer, there was another disaster inside waiting for him. Probably those first 3 or 4 months, I don't think he had a day where there wasn't some crisis that he found, whether it was operational, financial, or through management. Clearly, in terms of taking over as an administrator, this is more than just a full-time job for one person. If we did not have access to the resources that Public Works had, in terms of bringing in the accountants, in terms of bringing in trained water service workers, I don't think that we would have been able to have survived. It also isn't cheap. You know, fortunately for us, we do have a neighbor, and we were in the process of building an intertie with that neighbor. Timing worked out pretty well. They were putting a main. It's one of those situations where there's a street that separates the two districts. Our main is on one side of the street, theirs is on the other. They're in the middle of doing a new main, and so we are just going to, at each street, do an intertie between the two. It'll be a metered connection, and they are, at this point, being very reasonable in terms of what they're going to be charging us for that. Once that intertie is in, we'll have a lot more flexibility. We'll actually be able to take a look at what's going on in the wells. We'll be able to do better flushing. We can start talking about some of those interim repairs to get the flow back to what it was. All of that takes money, however. Perhaps one of the more hidden costs are the what I call the legacy legal issues. The folks in that community are 100% convinced that there was criminal activity on the part of their board. I'm certainly not going to make an opinion as to whether that's true or not. But there have been some lawsuits filed by some of the customers. And even though the county is not liable, because we are the administrator, we have got to respond. And so the mere effort of producing documents has proven to be an extremely expensive, time-consuming, and a very frustrating level of effort for us. And that is something that we really didn't anticipate. But the legal bills have been far higher than I think we would have ever have guessed. Part of that too is you know, having taken over a private entity, what is the proper legal approach to many of the issues that, you know, when Sativa was not within the county? How do we deal with employees? How do we deal? What are the contracting issues? What are the mechanisms by which, you know, we can legally operate and keep things going? We found that these disadvantaged communities, at least here in Sativa, were very distrustful. They had not been treated very well by the water company. We did get, I think, some goodwill in coming in. That goodwill is rapidly evaporating as they continue to have periodic brown water issues. The other thing that we learned is the rush to dissolve the district had some unintended consequences. There was a great deal of flexibility that we had in terms of our contracting capability, in terms of the flexibility of how to maneuver administratively and managerially, that we lost when it became part of the county. All of the county procurement procedures, all of the oversight, all of the government code applied to everything that we were doing down there. And it made it a lot more challenging for us to actually address the issues that we were confronting. So that's kind of the big, broad overview of our experience at Sativa. I think, you know, when you come to the end of the day, dealing with the financial issues and understanding the scope of the effort that is likely going to be required anytime one of these small, barely functioning water companies is being taken over, that there needs to be an understanding just how large the issues are for such a small water company. If anybody has a few questions, I'd be more than happy to answer.
I come from LA. So one question, why didn't you convert it to a spatial assessment district so that the owners of the properties within the district would have been the source of income for the water district? Spatial assessment district, why wasn't that used?
Also, the intent of our board was to be sensitive to the economics of the community that we're serving. And the desire was that during our interim administration and the brief period of time when we're going to be the successor agency, that the rates wouldn't change for these customers. And so that was part of it. The other part, I think, is simply from a timing issue. We didn't want to be there that long. We want to be out as quickly as we can. And so going through the effort of trying to form that versus going through the effort of putting an RFP together and getting a successor agency in.
Okay, and then next. Of the people that were being served by the district, how many of them were renters versus owner occupants?
Yeah, I don't have that data.
Here's one of my backgrounds, that I say I was asked to review a low-income spatial fee for water supply. I said, first off, renters don't usually have a water meter. Owners do. They pass on some form of payment to the renters.
Well, in this particular case, nobody has a water meter. There are no meters in the district.
Well, then the allocation should be to whoever owns the water connection. There's a connection, no meter, yeah, connection. I think Sacramento's the same way, no meters. But it's an issue that, for me, it's affordability. You were talking about so that the rates wouldn't change. Well, were the low-income renters actually paying the direct water rates, or were they paying something that the owners of their residences were passing on to them?
Yeah, I don't know what the relationship is if they were renters, what they might have with their landlords.
See, that's one of the issues as to if you get money from someplace else, who's going to benefit? The owners or the renters? Usually owners. How do you pass on some sort of benefit to, as you pointed out, low-income residents, but they're not owners?
Well, I think you start with not giving them brown water. I think that's the beginning point.
Maybe another question?
Who do you expect to have an interest in bidding on taking this place over if there's more money leaving than coming in by about $100,000 a year?
Yeah, so the one saving grace, all of the groundwater basins in Los Angeles have been adjudicated, and all the groundwater rights have been established for decades. The groundwater rights are estimated at about $10 million. So that's the carrot that's hanging out there.
Great, thank you so much, Dan. That was great. Thank you.
You bet.
So batting cleanup today is Dr. Carl Longley. He's an emeritus professor and dean of engineering, and he is a founding director of the California Water Institute at California State University, Fresno. Dr. Longley earned a Bachelor of Science degree from the University of New Mexico, a Master of Science degree and Doctorate of Science degree from Johns Hopkins University, and he is a California registered professional engineer. Dr. Longley has been a board member on the Central Valley Regional Water Quality Control Board since 1989. He has been the chair of that board since January of 2012. So, thank you.
Thank you very much. Well, I feel just like Dr. Cohen did, except maybe a little bit more because he gave part of the information I wanted to talk about also. And I think we can go home. I stole that from you. I do want to though comment on the slide that was put up by Kevin Berryhill where one of the bullet points was greater coordination between the Division of Drinking Water and the regional boards, and he went on to explain that it has improved. He was talking about my board, the Central Valley Board, that now there is a low-threat waste discharge permit out there. And I've been told, recently I was told that throughout the state of California, there are, first of all, more field offices for Division of Drinking Water than there are regional board offices. But I've been told that in as far as possible, where they tend to be in the same city, yes, Clay and Fresno, that there's going to be an attempt as leases expire to consolidate them. And with that, Clay gets up. No, he's coming down front. Okay. But I think that's important, and I think that we have a toxics office in Fresno, and they need to be sitting, I think, in the same building too, because when people sit together, there's more coordination. And a little bit later, when I'm talking about RECRA, it becomes pretty evident why I think these folks need to be sitting close to each other to coordinate. If you see them at the drinking water fountain, you're much more likely to talk to them than if you have to drive across town. With that, figure out how to operate this thing. Not that way. Whoops. Hey, there we go. Well, the Central Valley Regional Water Quality Control Board has a mission, obviously, to protect the environment, public health, and all beneficial uses by protecting quality of California's water resources. But go down to the very bottom. The regional boards issue permits which govern and restrict the amount of pollutants that can be discharged into the ground or into a water body. And so wherever we have a discharge, and that can be from a water treatment plant that is treating water and has a waste stream as part of that, that waste discharge has to be permitted. And that's where we get involved. In the Central Valley, a lot of waste treatment plants, particularly those in the Tulare Lake Basin, since there is no stream flowing out of the Tulare Lake Basin, except one could argue the Kings River does from time to time. Land disposal is an accepted practice. And of course, the regulations from this are found as shown up here. You can read the slide as well as I. But these regs have both prescriptive and performance standards for waste containment, monitoring, and closure. And these requirements are implemented through what I just discussed, the waste discharge requirements, the DWRs. They regulate disposal of discharge of land of certain solid and liquid waste, and I have listed down there amongst the 4 bullets hazardous waste, but basically hazardous waste cannot go to a permitted landfill. In general, these wastes cannot be discharged directly to the ground surface without impacting groundwater or surface water, and therefore must be contained to isolate them from the environment. And we're talking about haz wastes here, wastes which are of particular significance when we're talking about constituents such as arsenic. Not so much with certainly not with nitrate, because I think Dr. Cohen pointed out a very important factor about the nitrate. If you put it in an anoxic environment, such as a septic tank or certain types of waste treatment facilities offer, it goes to nitrate. The nitrate goes to nitrogen, and your problem goes away, so to speak. Well, what is a RCRA hazardous waste? And EPA defines solid waste as garbage, refuse, sludge, or other discarded materials. And that includes solids, semi-solids, liquids, or contain gaseous materials. And if a waste is considered solid waste, you have to then go through the exercise to determine whether or not it's a hazardous waste. So I list some characteristics of hazardous waste, but we don't stop at RCRA. The California Health and Safety Code is also very important here and goes much further than RCRA does, additionally designating a large number of constituents, both in liquid and solid media. So you have to read both documents and get the total picture in California. This slide is here simply because this is a RCRA 8 metals, and there's some materials here which are of particular interest to us. We're talking about today. Arsenic is the biggest one. I might point out that that's an old number. It's 0.01 milligrams per liter now, not 5 milligrams per liter. Barium, cadmium, chrome, lead, mercury, selenium, and silver. We have selenium in some of our waste. Certainly chrome-6 is an issue in this valley. And so the inorganics include metals such as, or inorganics such as arsenic, nitrate, chrome-6, and possibly some others. Organic pesticides and solvents, we have 1,2,3-DCP, which has been talked about today, but we also have still some number of sites with EBCP and pyrethroids and so forth. And then radioactive elements such as radon and uranium, which were discussed earlier. We've also discussed the human right to water. This is a slide from an earlier presentation, not this session, but I think session 1 or 2. And it's an important part of all of our discussion. And the selection of the water source becomes very important. And I've listened interestingly to what's been said today about pipes. We don't want to run pipes very far. I noticed that in the Midwest, in a number of states in the Midwest, and they had a lot of money at one point funding come into them from a number of sources. Probably the Bureau of Reclamation was the greatest, but there's a lot of some EPA money spent and some Department of Agriculture money spent. And establishing rural water districts, rural water systems. And these supply water in small diameter pipes, not to be used for irrigating your lawn, not to be used for irrigating crops or anything of that sort, but simply for in-residence use. And I'm happy to see that Division of Drinking Water is now looking at some of those systems to get some of the information on how they operate and to provide some basis of things that we should be considering when we're here in California. The problem with this, with putting in a system in this state, though, goes back to, and I'm looking for a statement, I wrote it down. I don't have it immediately here, but it was, I think Dr. Yoram's slide talked about the willingness of the inhabitants to participate in a plan such as that. I think that's something that the legislature has to consider when we have drinking water, which is dangerous. To what degree are we going to permit the continuance of supplying that water when people's health is at risk? And the way that is addressed, I think, is going to be critical to what kind of a solution we get in the future and how affordable that water is to the particularly to those in disadvantaged communities that have low income. You see this much the same thing occurring in a sense, with mutual water companies. And the folks that this is where the water company is owned by a group of people. Oftentimes it's not the people who are consuming the water. There has to be some reckoning at some point if we're going to get our hands on this and not let this calamity go on from year after year after year without addressing it most likely through legislation, and that's the only way that I know how to address it effectively. But the selection of the source water is extremely important. And I say in the second bullet that it must be that the selection of the source water and the preferable treatment must be made through a competent, thorough engineering, cost analysis. And that's another way of saying a feasibility study. Those studies are extremely important. How they're carried out, the thoroughness of their conduct is critical to ending up with what your goal is for that particular community. Then I state here that RCRA enters the picture, and we're talking basically, I'm talking basically about, although I get off track a lot, about residuals and what we do with those residuals. And particularly where we are producing a stream of water, which typically occurs of a system of any size, if we have consolidation, if we have this issue of RCRA and the costs that are associated with it. I'm getting ahead of myself here. In this slide, what I really want to talk about mainly, and you can read the rest, but the considerations here, the technical management financial capability, the TMF is so critical. You can't achieve TMF, the T part of it certainly, and probably the management part of it, if you have a part-time operator. My experience where I've seen in the Central Valley with part-time operators, they're typically grade 1 operators. They're looking for another job and they're gone soon, and the small utilities without an operator for a long period of time. You have to have a utility that is large enough to be able to support a competent management structure and certainly provide the whole TMF capability to that system needs to be able to have continuity and sustainability for a large number of years. With that said, and I'll be talking about it a few more moments, but I like Dr. Cohen's concept where he pointed out that in fact you can manage this system from a distance. And I've been pointing out for years that you can manage 20 systems from not a very large room, simply with the technology that's available today. Certainly the technology that he's demonstrated, that UCLA's demonstrated, can be used in these systems. So I think that it can be done. I think the more difficult parts are creating the legislative momentum to be able to get the rules in place to allow us to fully implement these kinds of systems. Because you could take a bunch of rural communities that aren't near anybody and manage them, and I think that not doing so is a terrible thing. Down here at the bottom, the next to last bullet states avoidance of hazardous waste concentration in a residual stream with a question mark. When you're concentrating up, more than likely you are going to have a hazardous waste concentration. You're discharging that, as already been pointed out by not only myself but other speakers. You're going to have an issue that you have to contend with. You can address this possibly with nitrate by blending. Certainly we talked about consolidating systems getting big enough so that you have the TMF capability to manage that kind of a stream. The consolidation is typically communities that are close to a larger community are brought into that community. But as been pointed out today, there's another way to achieve that using technology. And I think we need to look at that latter method with much more acuity than we have. Certainly when you talk about the development of a regional system, and we do need regional systems. We've talked about use of PUE and PUU devices, particularly with the PUU devices. the POE fit into the development of a regional system, certainly, so I'll let that go. But on the POU devices, there needs to be some sort of oversight by a management entity for the very reasons you've already heard. And I like the last bullet that Kevin didn't mention, and that's, he didn't discuss it, that's the beasties and other things. But there are a lot of reasons. Going into homes from time to time is not the answer. As was pointed out, those systems are not being monitored appropriately. So we talk about residual cost factors. First of all, is it a hazardous or non-hazardous waste? And if it's a hazardous waste, your costs go up tremendously. There is a EPA study some time ago, 1996, which is over 23 years ago now. You can find it on the web. And there they listed that the cost was on the order of $200 for a 55-gallon drum of liquid, or $60 per ton of solid waste. And however, there was a paper from 1996, Rooney and Reed study, which showed that the total disposal costs were only about 15% of the total waste cost. In other words, 1/6. So you can go out and get a quote, but you're going to find that that's just a down payment on managing those costs. The other costs are things that you have to do yourself in-house. Such as labor, sample collection and analysis. All the paperwork and tons of paperwork go with RCRA. Anyone who's dealt with RCRA waste will tell you that. Permit fees, the consultants you have to hire, and other costs, and it seems to go on and on and on. I think that this is reason enough to ensure that you have a very competent feasibility study, picking out which alternative is right. Concentration and quantity of hazardous waste is obviously important, and mixtures create more problems than if it's a single constituent that is causing the problem. Whether it's solid, slurry, or liquid also has the costs, and transportation costs can be tremendous. So to give one price for what it's going to cost to handle the waste from a particular site is almost impossible, given all of the site-specific factors that are in play. I point this out simply because the EPA did put out 12 years ago now a document which talks about the cost evaluation of POU and POE treatment devices for small systems. It goes into some detail. I'm not reading this, but particularly the left-hand column gives an idea of some of the things it gets into, both capital costs and O&M costs, but nowhere in there did I find anything about handling of residuals from the facility. Point of use devices, as was pointed out, it typically goes into the household waste stream. In the long term, that's not good, but that's where, in fact, it does enter, particularly if the individual is changing out their own unit. And the POU devices themselves, for me, are problematic. I think we've talked a lot today, particularly in this afternoon session, about what's not so good about POU devices. And certainly all the reasons that Kevin Berryhill and Dr. Cohen mentioned, I endorse. I think that the safe disposal of these units over the long term is an issue and could become a issue someday for individual users. The the quote that from Kevin that I missed, the bullet was the problems with these devices also is cats and other beasties. That was it. Dr. Cohen's virtual POE system, I think, has great appeal to me since it provides the necessary oversight without the necessary high costs associated with many of the other alternatives. I would make one exception to his comments, and that I believe the technology he has for control and monitoring of that system could be retrofitted onto other package systems that don't necessarily use RO as the prime treatment process. In other words, if you went into a process for arsenic that uses coagulation, filtration, and so forth, I think that that system also could be fitted with the same kinds of technical controls that Dr. Cohen so well showed for his system. So with that, are there any questions?
Surface water that we worried about in terms of being contaminated. The surface water treatment rule and the disinfection byproduct rules and such were put there because we worried about surface water, and groundwater was generally thought of being more pristine. But since the 90s and such, as we've worried more on arsenic and then nitrate and hexchrome and all these other things, we're seeing the perfluoro compounds, that's kind of switched. And you were talking about legislative changes with respect to consolidation and some of these other things. What opportunity would we have for source trading? That is, for some of these small systems with junky arsenic water, that we could get them onto surface water that would be a lot better, where the treatment would not require disposal issues, and you could give whoever needed the arsenic water for their crops that water, which would be probably just fine.
Thanks, Bruce. You bring up an important point. I think we need to look at more surface water. Certainly the systems in the Midwest I'm talking about tend to use surface water. And they have more bigger rivers maybe, but we have canals that go all kinds of places. And the only downside to that is I'm familiar with some work that was going on in Tulare County, the eastern part of Tulare County, where they were going to take water from the Bryant Kern Canal most of the time, but the canal goes down time to time for maintenance. And so then they have to use groundwater. But we've seen already that, and there's some good examples of where groundwater recharge into these areas does improve the quality of water quite a bit. So if I think in many areas when you did have to switch back to groundwater, because you're probably going to need a standby source of water, that you might have a much better quality of water if you could store this water for when the canal's down. We have that. I think that's something that needs to be looked at. It has some downsides to it, being the fact that you don't always have that surface water source. But it's true. If you can get surface water, I think it's preferable. Obviously, you have to treat it, but the treatment processes typically are much better known, or typically not as expensive, and you don't have to deal with these contaminants typically.
For the Fresno area, has there ever been any special assessment districts formed by the counties or the cities regarding water supply?
That's a good question, and I don't know the answer. I'm not aware of any.
I don't either. Also, one comment on point of use, point of entry is, didn't we go through the water softener issues once before, and the sodium issues as to what it does to treatment plants and things like that? So I say point of use, I've built water filters overseas for our staff. And I say it's always a problem of operations and maintenance. And I say, yeah, you could probably get a company maybe that could service maybe 10,000 units. But when you're working on 100 buildings, maybe not so much. So I might say point of use, point of entry always seems like we're passing it over to somebody else.
Well, the point of entry, I don't have as much problem with if it's the system as described by Dr. Cohen, because it's really a small treatment plant. It's outside of the residence. It's serving a number of residents, quite possibly, and you can control that thing from second to second, quite frankly. It's the point of use that I really have an issue with. By the way, there is an issue with point of entry that I would like to mention. Some years ago, on a contract from federal EPA, I was looking at the use of carbon for DBCP, and we came across one home, which I won't name the name of the company that was servicing this unit, but their plumbers, when they plumbed the thing in, had mistakenly bypassed the filter, although the people were getting charged monthly for the use of this. It was a GAC filter, and they were getting the full load of the DBCP in the home. So cross connections and plumbing are always something with any of these systems we have to be careful about. And also the comment earlier on the fact that there are salesmen out there that that oversell their product is absolutely true. I had one come to my home back about 1985 or so, and he was telling me that a regular water softening device could take out DBCP. He should have been suspicious. When I went into my office, my home office, he came out with a legal pad and started writing. But the net result was that he eventually had to explain himself to the local district attorney's office. You got to be careful on what's out there. They certainly oversell themselves.
Yeah. Okay.
See if there's any questions that came across.
So I didn't see any, but I had one of my own. And that was, Dr. Longley, do you have an idea of costs or references that we could use for costs for disposal? I saw the POU one. Is there something else as well?
If you go to the literature, first of all, go to Google. And you'll notice about the first 5 or 6 on the topic are ads. The information you get is all over the place. I'm not aware of any good study outside of the Ohio study. And that study was, first of all, is rather old. Secondly, it was focused on companies and not on residents and not on households. But I think it does give, because some of the costs would be the same one way or the other. And I think it does give a pretty good idea. You got to be careful, too, when you look at costs carefully, because in the small print, some places they won't handle hazardous waste. They'll only handle non-hazardous waste. Okay. There was something that I didn't look at, didn't have time to get it done, unfortunately, but there was one needs to look at what it costs the Corcoran to process their sludge, their arsenic sludge. It's not quite the same, but it's still a lot the same as you would get from a drinking water treatment plant. Well, it is drinking water. It is drinking water. So, but it's sludge from that, and that would give you some idea. It's a larger system, so they may get some benefits from that, but it's my understanding that they do have to go to a hazardous waste site.
Okay, thank you.
Davis project, there's some, as a part of the Prop 50 UC Davis nitrate focus project, there's some continued survey of waste disposal costs. I will just say that over the last 10 years, there's been a significant variability in the costs of disposal as different options for where various types of waste, whether it be high strength hazardous, low strength hazardous, high strength non-hazardous, and as you get progressively cleaner in the waste character, the degree of where those things can go. Some of the places where some of those intermediary classified waste, if you want to call them that, have gone away, which has pushed those volumes to the higher classification locations, which is driving up those costs. The other thing that's driving up costs is both the labor and the transportation costs associated with getting them there.
Yeah, labor and transportation are a big part from what I saw.
Exactly.
But I think what you get to, it becomes very site-specific based upon the type of waste.
It really does. And that's where, the focus of the Consolidated Management Project is so keenly attempting to overcome those hurdles. Simple things like if you're a small system that needs to dispose of waste every 30 days because of some regulatory driver, but in 30 days you only make 1/10 of a truckload, but there's 10 other ones around you. You can't put that all in the same place until you get it to the location it's to be disposed of and characterized. And so there's some administrative things we're going to try to attempt to see how we can overcome those barriers, gain those economies of scale and those efficiencies without tripping over the black and white regulatory.
And I think that's needed. I think it's very good for the short term. I really think in the long term we should be looking at ways to get better quality water. I think that the idea of going to surface water, even if we have to take it quite a distance, there's a point there where the cost factors are going to tell you, no, you don't want to pipe it that far. But we're putting more and more canals around the valley. So, yeah.
I'll ask a question. Actually, just a couple of quick points that I wanted to note that I've thought of throughout the course of the day with good examples of ideas that could be considered in California that come from other states' experiences. The greatest large-scale regionalization efforts in the country come in North Dakota. They have 13 regional rural water supply districts that supply water for hundreds of miles in each case. It has come from a number of very large-scale federal appropriations, and they're kind of highlighted as a great example. Whenever I've talked about those options here in California, typically we run into questions of seismic challenges and reliability and redundancy, and CEQA being key limitations that would preclude it from being cost-effective. But I think it's worth thinking about that more.
Could I comment on that?
Yeah.
I agree with you, and North Dakota is a unique example because I was told by the Bureau when I was looking at getting funding for them for a system at one point, that the North Dakota system occurred as it did with all the federal funding as a buyout from the fact that they were planning on building a dam, but they ran into problems with international treaty between Canada and the United States. But also, but with that said, you go down and look in South Dakota and Iowa and in the Midwest states, you'll find the same thing with hundreds of miles of line. Nebraska, as an example, Nebraska has a huge problem with selenium in its groundwater in some areas. So yes, I agree with you entirely.
Yeah, good examples there. There's 3 other specific state examples that are worth considering. So Colorado, at the advent of the arsenic regulation, some ways in light of what Kevin was talking about Los Banos having, all of its wells impacted by arsenic and not knowing, or by chromium-6, for example, when that MCL came out, and how to overcome that. When any given new regulatory driver comes out, there's an opportunity to provide a consolidation of technical advice about how to address those things instead of the one-off, one-over every time in every place it's implemented. Colorado did that for both arsenic and for the radionuclides rule implementation. So they had a statewide effort for all the smaller systems that couldn't do that on their own, have a cohesive effort statewide to address it, and good consolidation of that. And I think it simplified the regulatory folks' efforts to approve what would go forward, kind of bypassed all the California State Drinking Water Revolving Fund Planning Fund approach. The next one is in the areas of innovation and how to get commercialization of technologies in a California-specific context. State of Nevada 4-ish years ago started what they call, it's now coined as the Water Start Fund, state-funded effort intended to bring innovation to the state. They grant monies to commercial businesses wanting to commercialize technologies in the water space. If they succeed, there's a expectation that they then house their business in the state of Nevada. Clearly, there's differences in the business climate in Nevada and California that can drive that, but there's some very specific California-specific needs that I do not think will happen commercially unless the state encourages it. And so there's going to be some needs to push it that way. But the Nevada example, and actually the accelerator in Hawaii is another good example with Elemental Accelerator. And then the last one that really struck me, I hadn't thought much about the point of use, point of entry approaches and how we could use fit for purpose water. Alaska sponsored a program 3 or 4 years ago called the Alaska Water Sewer Challenge. And the whole point of that was small systems that rely on trucked water, both clean water being trucked in and black water being trucked out, wanted to improve upon the efficiencies of those water haulings so they didn't have to truck as much in and truck as much away. So they sponsored a competition, 3 different teams submitted on it, and they had some really successful outcomes where they start using the fresh water for freshwater purposes, potable drinking water and bathing, cooking. The next tier down of water that was an outcome of the first treatment process was for household cleaning, washing, not food, of course, and then progressively degraded, if you would call it, water quality all the way down to toilet flushing and black water. And they garnered really extensive improvements in efficiency that perhaps could drive some of the costs lower in some of the point of use systems that we have here in the state, as well as overcome the challenges of increasing water pumping just to overcome the efficiency usages in the first place. So all those things I think could take on a California flavor and gain a lot of momentum here.
Thank you. Maybe other questions? Dr. Longley or any of the question here?
Not really a question. A basic element, when you start talking about costs, I always go back as to who's going to pay them and who benefits. And I'm still very concerned with, being asked as to, well, low-income water connections. Well, I said, first off, if you're an owner of a water connection or meter, you own a house. So by definition, you are not low income. However, you're renting it out to somebody that may be low income. So I'm always concerned, follow the money. Where does the money come from? That is, who pays? And if it's the state of California, then everybody's paying, low and medium and high. And the question becomes as to who's going to benefit from having a better water supply. Cheaper water, does that go to the owner or the user? Because the users are going to be generating the tax revenue, which provides it to the state agencies to distribute it. So I'm always concerned about Who benefits? Who pays?
Yeah, no doubt, but I will tell you, it came as a surprise to me as well. Because you own a home or property does not mean you're not disadvantaged. We discovered that a lot during the drought. There are a lot of really stranded properties that people really simply can't sell because they're in zones of which are all disadvantaged and stuff. So yeah, so there's definitely a component there. I also didn't realize how much. Just because you're in a home, that how much of them are rented, and there's a lot of them in the Central Valley that are rental properties. And so I went in with the original attitude of like, well, let's get after the slumlords that are creating this. Well, a lot of them are grandma that has this stranded property that rents it for $5 to the cousin who mows the lawn and keeps it sort of looking nice. And there's a lot of arrangements like that that really complicate that issue. So it's not simple to parse that out in any way. So, but yeah. You gotta parse it out because well, ultimately in California, the way we have it set up now, right, is that there's an expectation that a water system itself has to be self-contained and self-funded. Now, that's a big question out there with the Safe Affordable Drinking Water Fund Act. We know there are communities that can't support themselves in that particular model. And so we're talking to the legislature needs to contemplate whether that's something that needs to be changed or not. So it's a very big discussion for sure. Yeah.
Perhaps just a quick comment and maybe a hope that in going through this exercise of doing the analysis, the costing for various alternatives, to urge you to look at the most current technologies, also look at the potential for what may be coming down the pipeline, because if we rely on what's in the EPA manuals, which is old technology, I know that people say membrane is a membrane is a membrane, but that's not true. There are other elements that allow us to improve process efficiency. And the other is to look at uncertainties. And by that I mean to really understand what leads to the highest deviations or ranges in the cost estimates that we have, so we understand what those factors are, so that decisions are not being made without understanding the uncertainty. So that's, in my view, critical. And one thing that I've not heard, although I mentioned it, is when we look at solutions, it seems that we focus here a lot on technical issues, but the legal and permitting issues are also significant and add to the cost, and somehow, I don't think that we're paying that as much attention. And if we go to small communities, I think that we need to understand that they need to be looked at, regulated perhaps in a different way than the large systems.
That I'll disagree with. No, from a standpoint of regulatory construct, we get that a lot of times, but I think there's an expectation that everybody has the same access to safe water. So you get into really soft ground when you stand on, well, maybe we'll test them less. It's like, well, but then your certainty of water service goes down and other things. So unless I'm misunderstanding you, it gets really hard, in my opinion, to be separate.
Yeah, I think there was a misunderstanding. I don't mean that they're tested less. I think that in the process, because a small community does not have the same resources as a large community to even comply, in a way that makes sense. So how is it that we're going to deal with them? Are we going to make it easier for them to go through the process? Not that we're going to give them a buy and say, you don't have to comply. So,
yeah, no, I know what you're saying there. So I guess I think the one thing that's really important, and I think that was in some of the presentations as well, so I was happy to see it, is that, and I'm a big advocate of this is part of the stump speech I often give on the topic like this, is that we really have to change water utility delivery in California. And when I look at it, no matter how you cut it, when it's 100 or 200 connections, in today's age, it doesn't make sense. And there's just really no way to get at it. And so we need to understand that we need to respect the community needs to come up with something different, but we need to be very clear that, you know, at those really small connection rates or sizes with, you know, compromised water quality from groundwater and other things, what was a successful model 60 years ago of drop a well and pay the electric bill doesn't work. And so, you know, we have to really morph and change the approaches, and there's a lot of people that talked today that were talking about how to enter that space, so definitely. And I'll go back to kind of one of your first ones too. Technology is definitely there, and over here, the state sucks at a technology innovator, and what happens is, we've been down this road many times, and it's a great suggestion, but the taxpayers have zero expectation that we spend money and it ends up in nothing. So they always look back at us. It's like, well, that was wasted money. And it's like, well, yeah, but I mean, a capital investor over in the Bay Area, if he gets, you know, 1 out of 10, he's like a really successful, and everybody, you know, praises him. And if I get, you know, 5 out of 10, somehow I'm a huge failure from a government manager standpoint. So that's always tricky. Certainly, we'd like to create the space for that to happen, but being a direct funding is always difficult for sure. So we're always held to a different standard on that. And I think Greg had a question, didn't you?
I really appreciated your presentation, sort of digging deep into the Sativa case. I was wondering if there were any warnings, like TMF warning signs, that you think could be generalized in the context of the needs assessment that would necessarily be sort of broader brush. The ones I heard were perhaps the flat rates, no meters, and then no intertie, but other sorts of metrics that could be derived from a broader brush assessment that might, you know, help us to catch sativas before they become what it became.
Well, I think, you know, the fact that they didn't have meters should have been an indication that they were in financial trouble, if nothing else. You know, part of the problem is that a lot of the reporting is self-reporting, and I won't say they were cooking the books, but I don't think they were 100% truthful in the reporting that they were doing. And unfortunately, you can find certified folks to sign just about anything you want if you pay them. So it gets difficult. In terms of oversight, you know, the more you have, the more expensive it is for the rest of us to foot that bill. But probably in this day and age, if you've got a small, especially urban water company that doesn't have meters, I think that's probably a pretty good indicator you got some problems down there.
Thank you. So actually, I want to add on to Dr. Cohen's comments. I think I'm experiencing it with him for the permitting, actually, for water systems or for their project. They're coming in to operate and put in a treatment plant. And how do we permit such a system? Because the owner of the water system, they own the well and they own the distribution system. How do we insert a third party in the middle to come in to take the water from the water system, treat it to drinking water quality, and pass it on, and how to delineate the roles and responsibility and how to permit that? I think that's probably forward thinking, that in the future we'll have a lot more of these third-party role coming in. They don't want to gain all the responsibility of like leaky pipes or something downstream of it, or when the well fails, but how to fit it in and be able to permit them and give them some assurances that you're coming in to help, but you won't be held responsible because you're now giving it pressure in the water and you're causing all these leaks in their distribution system, or how to protect them. I think that's part of the discussion that we need to look at. So it's not just treatment alone, it's what happens to the upstream equipment that may need some upgrading, and then downstream distribution system as well.
Hi, thank you guys for hosting this session today. We appreciate the board doing this as a 3-part series. My name's Melissa Sparks-Kranz. I'm with the Association of California Water Agencies. And I think we're all of the folks in the room and those online are here invested in coming up with a well-informed and solution-oriented needs assessment. I think a lot of my comments are going to be forward-thinking. I do appreciate the very technical information shared today. I think it's part of the solutions, but we're interested in understanding where the State Water Board is going to go next with developing the statewide needs assessment. So, you know, how are you thinking through, how is the board thinking through developing the solutions for systems and then estimating those costs? You know, how are you going to go about determining what's a consolidation solution for a system, what's a treatment solution, and the cost estimates associated with that? I think that's a big question still for us as to how you're going to proceed. So we're interested in that. I think we're also interested, and it was brought up today, about new MCLs and building in those costs and how to address those moving forward with the needs assessment. We don't want a needs assessment that's a one snapshot in time, but are we building methodologies and assumptions in this process now to account for future MCLs that are going to come into play and addressing those needs and those costs? I'd also just like to add that I really appreciated the financial assistance presentation earlier this morning about the planning projects that you guys have already gone underway, and that you have TMF assessments with those projects, and you have cost assessments or cost estimates for those systems. I think that's a helpful place to start when we start thinking about all the systems that need to be addressed within this needs assessment. I know that DWR has another program, the Disadvantaged Community Involvement Program through IRWM. They are doing regional needs assessments as well in disadvantaged areas. So is there a way to leverage other needs assessments that have already gone underway or that are going to be potentially could be incorporated into the work that you're going to be doing? So just a few thoughts. And again, I know those are questions that you're probably going to have laid out in your conceptual plan, and we really appreciate the fact that you're going to be doing, you know, public opportunity for comment on that as well. So thank you.
Yeah, so what's next is, you know, we'll get together with different folks that, you know, might be our contractors and experts that will advise us, and we'll try to put together some draft scopes and share that and see if we can get some comments on that. I think, though, one of my takeaways from today is we're going to have to rely, I mean, I won't be able to tell you exactly the method going into it. If that was the case, we wouldn't even have to have the day, right? So there's going to be a lot of, okay, we're going to hire experts that are going to try out some things and then focus in through their work on what might be working and not working. And that, you know, will be a bit of the body of the process. The intent is that while this will be a one-time snapshot, that, you know, the Safe Affordable Drinking Water Fund, if that does come to pass and is before us, it has built in an ongoing needs assessment on a routine basis. I think it's every other year type of an approach. So there would be a continuous rolling factor of that to be able to inform the fund and move forward. So I wasn't really anticipating trying to have this needs analysis be, you know, 20 years out of all the MCLs that could come our way, because that would be, if I had that crystal ball, I wouldn't be here. We'd be playing the lottery and other kinds of really more productive things for that. But it's a good point. There will be more costs, definitely. I think there's just that always trend of you know, increased understanding of the contaminants we face and what we need to address. So there's certainly that aspect of it that we'll have to contemplate to some extent. And I think that is contemplated in part of what I said earlier about small water systems, because they struggle with the first increment of challenge, and we can pretty much guarantee that a lot of them are going to face more challenges, and therefore, how do we build a more robust water utility sector that can address that and be responsive to that and be prepared for that going forward? That's just really part of my thinking long term. That has to be part of where we want to take everything and what the information we develop now to inform all the local decision makers that have to make those hard decisions later going on. So it's going to be hopefully transformative in everybody's thinking and provide information for all to make steps in those directions. So it'll be a long conversation. Is there any other questions, or should we let you have a weekend?
So I have one more question, Darren.
Yeah. Sure.
So I have heard lots of people say they want like what was it, solutions-based needs assessment. And I'm just wondering if anyone in the audience can sort of define that for me. Yeah, I think it was you that said it, but I wasn't going to put you on the spot. But I've heard it in several different contexts.
So I think I would differ from maybe what Darren, what you just offered would be the result of this $3 million assessment would be a one-time snapshot. And I think what I would encourage you to pursue is a way of thinking about and addressing the problem for here moving forward, so that the next maximum contaminant level, that there's kind of an agreed upon idea of how to look at that you could use that in evaluating the impacts of new standards, new maximum contaminant levels. But in terms of the needs-oriented, in terms of affordability, not to draw just a bright line at a certain level, but to have within the analysis the ability to evaluate what are different ways of making the providing the maximum benefit to the most vulnerable. So not just constraining yourself to 1.5% of the median household income. Being able to look at various ways of defining whether a system is successful or not. We heard in one of the presentations about very specific how many quarters that one would be out of compliance. So a system so that we could not make that normative judgment, but could evaluate different scenarios. A system that was place-based or spatial-based, so that you could have a real good handle of how to connect the systems. So I think that's really the heavy lifting, is to come up with a methodology that kind of the community would agree on, that would be useful for finding those abilities to solve the problem, as opposed to just getting a dollar amount for how we might think about solving the problem today. So is that helpful to your question?
Yeah, and I think that's what we have in mind. We may not articulate it very well, but definitely the needs analysis isn't going to be a dollar, isn't going to be a, hey, it's this amount. It's going to be a whole investment in a process that gets to be used over and over again. Definitely, if we haven't said it enough, from the beginning, the hard part for me was not to just say, hey, we need treatment, what's the cost? Because that's easy, but it's wrong. The answer's wrong. That's way too expensive, and it's not the path that we would pursue. And so it's exactly looking forward, like, okay, well, we do need to contemplate consolidations. We do need to say they're going to do more efficient forms of management, so that's the cost that we do, and I think that does drive those solutions. So I think we're on the same wavelength when it comes to what you said. Absolutely. The professor always has to have the last word.
Some of the factors that he had, but in the analysis, I think would be very, very useful to have to accommodate potential growth. In other words, if you have a solution, because the small communities that we're talking about are small. So if you talk about a community that has 10 people, 12 people, if it doubles, is the solution that we have or contemplated going to be obsolete or not workable? So I think somehow we have to build that uncertainty into it.
That's always a tricky one too. And so when we were with one of the earlier workshops, when Jeff Hughes was here from North Carolina, he actually uses an indicator for them, declining population, as one of their risk indicators, because a lot of these small communities are really shrinking. We're urbanizing and the rural components are going down. And so it was like, he was more worried the other way. But there are both constructs to contemplate, and growth in either direction or shrinking is a complicating factor for sure. Definitely.
Darren, I think there's one other thing that needs to be addressed, and Dr. Cohen addressed it earlier to some degree, I think, but you were in the discussion about the difficulty in California of you're successful in 5 out of 10 and you still got a problem. I think we have to find a mechanism to address technology in California, much as the Air Board, much as the Air Board does. They've seemed to have a pretty good working model. I think we need to find how to do it within the water boards.
Okay, well, there's a challenge. I wouldn't debate it as a definite positive outcome if we could figure out a way to.
I think it needs to be on the list.
I do always want to caution though that, you know, while I'm definitely an advocate of technology, I always am fearful because a lot of people that don't want us to move ahead on this are like, well, we'll just wait for the technology to improve, and we can't do that at the same time.
Oh, you're right about that.
Yeah.
But there's a lot of technology out there that's not even being considered.
Yep, no, absolutely. And I think that also factors into water system size and capability or regionalization and those type of factors. It's a whole piece of that bigger puzzle coming together to try to move it into a different future for water utility. So, all right, I think, okay, one more. Sure, why not? You all spent all day. Yes, thank you, Dan. Don't miss your airplane.
Have you ever used SimCity?
Yeah, I used to play it a ton when I was a kid.
I would highly recommend that.
You have a sim water system?
We have 5 days until the presentations are online. That during the 5 days, figure out might say, Waterville model as to all the problems that you've seen, put them in. And then have people react over 2 weeks from whenever the presentations are out as to, you know, specifics as to try this, try this, try this, try this. Because you have a vast audience, and it could be even vaster online, to try to come up with any sort of innovation. Because if we wait, that's one thing. If we lead, that's another thing. So you might say, we have a problem. It's common in my area. One of the community plans, they show a declining population. Why? Because everyone's over the age of 65 and there's no new blood coming in because Prop 13 has fixed everyone in their house because they can't afford to leave and they're not qualified for a new house loan. So things like that are coming in, and might say, I've worked around Coalinga, Avenel, and a couple bars in the Coalinga Hills, and they have problems too. And might say, basics, if I can't drink the water, what do I do? I'd highly recommend compose a problem town, Waterville or Waterton.
So SimCity developers take note. We'll post it on our website right now if you can get that.
And try. There's a lot of good water engineers, water planners. We've been doing it for a long time. I remember before the State Water Project, things were different. And try to take the lead and try to distribute it out. So.
Well, with that futuristic thinking, I think I'll let you all go home and have a weekend. I appreciate everybody coming and the presenters. Thanks to Chad for hosting and Michelle and all the people that helped her put this together. It's been super important for us to do this, and it's quite a body of work, so thank you all.